Yeah. Okay, so hi everyone, and welcome to the final presentation session for the QCourse551. It has been really a great experience, I think, for all of us, but from my side, it was really nice to see the work and progress. So first of all, thanks for QWorld and for Abu specifically for the opportunity and for the collaboration. It was really nice. We started collaboration before this course, but I think this was the most intense collaboration. It was really nice. So thank you for all the work. And thanks to all the mentors from Classiq. We had some difficult times in Israel, but for those who stayed, so really thank you. I think it was really a very good experience for us, and it was really helpful to promote towards what we really want to achieve. And most importantly, thanks for all the participants and to you guys that actually made the work for the last 3 months. We had some challenges along the way because of bigger scenarios in the world, but for all of you that kept and finished the work until the end, it was really impressive and well done for that. So really it's great to see. Also, I think you did this work alongside significant improvements and changes in our product, and your agility and the way to adapt for it and to use the new QMod language and to adapt quickly to all the changes that we had frequently. So it was really nice to see from the side, and your engagement in the community and with the mentors and with the entire community was really nice and encouraged. So thanks for that and well done. I hope you understood the essence of Classiq, and I'm really waiting to see the final results and how you present them. And I really hope that you continue use Classiq because it will be super useful for you in the next projects that you do, in your research, in next hackathons, in the next educational tools that you use, and that will be great. And after finishing this Q course, you are basically starting to be Classiq ambassador. So you used Classiq for 3 months, and we had a lot of time together. So please talk about your work, have blog posts, discuss with people about Classiq, about what you do with Classiq, what you like, what you don't like, what you want to improve, what are the advantages. I think it will be really meaningful and good for you and for us. So that's great. Yeah, and that's it for the high level thanks and congratulations. So regarding today's session, we have 12 groups, and we have 10 minutes for each presentation and 3 to 5 minutes for questions. So everyone, please stay on time. I'm going to have a timer, and then after 10 minutes, I'm going to stop you. So make sure to, within these 10 minutes, to actually describe what you want to describe, and be aware of that. All the people here have basic understanding of quantum computing, but we all didn't do your specific work. So make sure you really describe what you've done to people that know what quantum computing and our colleagues, but don't know the exact knowledge that needs to be for your specific work. So make sure to bring the audience to this level. So make sure to be on time and the presentation to be for the general public. And when you present, you should open the camera so we can actually be more engaged with the presentation. So that's it from my side. Abu, I think maybe you want to say a few more words.
Yeah, thank you. It's always been a pleasure to work with Eden. He's always make me smile. He's always positive. Yeah. First of all, thanks to Eden. So our collaboration starts maybe even not 1 year, and we really end up with such an advanced project. So QWorld started more or less 5 years ago. And at the beginning, we had just workshops like introductory quantum computing and programming, single workshops. And but in my mind, always there are like some stages. Also on the way, people usually finish our workshops and they ask, okay, what's next? And this quantum software courses is one of the aim in my mind to achieve it. And finally, thanks to Eden, also Classiq, they were very open to this idea. And also they supported fully. They formulated 13 projects. 13 mentors, and now today we have like 12 presentations. So it was a like really great milestone also from QWorld side. So it was also kind of pilot program we did first time. We also learned a lot. Probably next editions will be more, let's say, matured. We also know better how to do several stuffs. I also would like to thank all students. So we really start like around 100 students, but overall course was online, and online course engagement is always challenging. Half usually disappear, it's always expected. So this was also designed as a like graduate level course, not like undergrad. So our expectations also were very high. So we also have like strict deadlines. We ask like weekly reports. Every 2 weeks they need to present like their progress on the online meetings. And I know that our students in this class also they like working. And some of them are already professor, researchers. Some are students, and they also have their like regular classes. Some of them also bachelor students, not like graduate level. Anyway. We achieved, and now we have 12 projects. I also would like to thank them once more, and also thanks to Classiq once more. Yeah, these are the things from my side. I hope such courses between industry and, let's say, universities will happen more. All around the world, several students or people just learning quantum, and they really want to do something. And such courses is exactly for this. You can really like develop some projects. Okay, these are the things from my side. We still have 5 minutes.
Yeah, I think we can start. So for the first group, the reduced hybrid HHL algorithm, group number 30. So can you share the screen?
Hi. Yeah,
Hi.
sure. Can you see it?
Yeah, we can see the entire screen now.
The presentation?
No, we can see the web with the Zoom.
Oh, now.
Yeah, now we can see. Okay, perfect. So during the 10 minutes, so you can ask question in the chat, but then we have 5 more minutes for Q&A, so you can keep your question for then. And the 10 minutes start now.
Okay, I'd like to invite my colleague Vargavi to start. I think she's muted, perhaps.
What is the name?
She's the second name on the presentation.
Yeah, I have access. Yeah, now.
Here, okay.
Well, thank you. It's a wonderful course so far. So our group, we were working on the Hybrid HHL project. And Bartos, me, and Rodrigo were working together, and Tomo was our mentor. Next slide, please. So the goal is to solve a system of linear equations, and the HHL algorithm is a quantum algorithm introduced by Harrow, Hasidim, and Lloyd to solve a linear system of equations. And usually the HHL algorithm provides an exponential speedup compared to its classical counterpart. And we were studying the hybrid HHL. Here, hybrid means we were using some classical pre-processing to gain some information about the problem and use it for next steps in the algorithm. And the idea is to compare this hybrid HHL with the original HHL in terms of several parameters like the qubit count, or whether you can improve the complexity of the circuit. And we applied this HHL to solve a particular problem, which is the Poisson system of linear equations. Next slide, please. So the HHL algorithm has 4 parts. First is the state preparation, which is followed by phase estimation. And then there is amplitude loading, and then we uncompute some of the phase estimation to see the results. So in the algorithm, this amplitude loading usually has a lot of multi-control gates, like you see in the picture below. And each multi-control gate has a lot of control bits. See, the idea is whether we can use some classical pre-processing after the phase estimation in order to reduce the number of multi-control bits and also the number of controls in each multi-control gate. And this is the rough idea behind the amplitude loading. Of course, there are like efficient ways to load this. Yeah, next slide, please. And what we were doing was previous slide, please. So yeah, we were analyzing the results after the QPE to gain some information. And if some of the bits were the same among all the qubits, we can treat them as classical bits and remove the control part, thereby reducing the complexity of the circuit. So yeah, next slide. And the next slide, please. Yeah, so after the classical pre-processing, here you can see that we only have 3 multi-control gates, and we also have just 3 controls in each multi-control bit. And now Rodrigo will introduce the Poisson problem and also explain how we actually managed to reduce the number of controls in the algorithm.
Thank you, Bhargavi. So we chose the Poisson system to be the mathematical setting to apply this reduction scheme. So it's as you know, it's a famous equation, the Poisson equation. The linear system comes from a discretization with gaps of the same size, and you get as a coefficient matrix this Toeplitz matrix here, which has constant diagonals, right? So it's only 3 constant diagonals. This matrix has a lot of properties. One of them is that you can know the eigenvalues analytically. So they are always in the interval between 0 and 4. They're monotonically increasing and undegenerate. So you have some information already from this mathematical setting, and we want to apply the HHL to this system in particular. So here on the bottom line, you can see basically what the solution is for this system, right? Once you invert, you get a superposition on the eigenvectors Vi of the matrix P with the coefficients B over lambda, where B is just the Bi are just the components of the right-hand side vector B along the eigenvectors of the matrix, and lambda are the eigenvalues. So I will be talking about these amplitudes here, B over lambda. So as you know, in phase estimation, you need the eigenvalues of the matrix that you're exponentiating to be between 0 and 1. And as I told you, the Poisson matrix is between 0 and 4. So you need to do some sort of rescaling. And what we found out for this system was something special, that once you do the rescaling, so you map the matrix to a new matrix such that its eigenvalues are between 0 and 1, right? And you have this rescaling parameter k, which controls the size of the range where the eigenvalues will be. And what we found out is that effectively the choice of k affects the number of control states you have. So in this table here, you can see that you have 2 choices of k for this is HHL for Poisson system with 6 phase qubits, so from 0 to 5. And depending on your choice of the rescaling parameter, you get different numbers of control bits. So here you have exactly 3 phases, control phases for each of the choices of k, each of them associated to a definite probability B over lambda squared. So you see that they differ greatly in how they affect the solution, right? And for each of one, you can see which bits of the control phase are equal, and then you can forget about the equal bits, and you do not need to implement the controlled unitary the controls for those control bits which are equal. So on the right hand column here, you see the representation of this reduced controlled phases without the unitaries being applied, just so you can see that you actually need a lot less control bits just for 3 eigenvalues in each case, right? So the depth here with and without CX optimization for you to see what amounts this choice. So you see that there is some reduction. Now, what is exactly the probability filter we are applying so that we can reduce the number of eigenvalues? So what we have is, from the hybrid approach, once you apply the quantum phase estimation, you get counts for each phase, right? And the total number of shots with which you can calculate the probabilities for each phase. And turns out these probabilities for non-degenerate eigenvalues are exactly the square root of the b's. So when you look at the first graph, you have for an 8x8 matrix, the red lines are the exact eigenvalues for the shifted matrix. So the lowest eigenvalue, 0, corresponds to the lowest eigenvalue of the Poisson matrix, which is around 0.12. And you see the blue tower is the probability B over lambda squared. So you see that it has the largest contribution, in this case, comes from the lowest eigenvalues. But what we're trying to do is select the highest probability eigenvalues, which is the same thing as saying, in this case, the lowest ones. And if you do that, and you run HHL, this reduced HHL, for the counting each eigenvalue once, like you run for 1 eigenvalue, then for 2 eigenvalues, and 3 up to 8, you see that the secret depth increases more or less linearly, but already with 2 and 3 eigenvalues, you have a good fidelity with these red crosses. So you see that by just using 1 or 2 or 3 controlled unitaries, you already get good results for this case. Now, let us compare the situation with the basic HHL using the best implementation that we simulated, which was amplitude loading with gray code. So if the first line here, the first table is for the 8x8 matrix, and the second is for the 16x16. And the first line is just using 1 eigenvalue for the controlled unitaries, and the second one using the total number of eigenvalues, so 8 or 16. And what you see is the depth is very close to the best, let's say, the best implementation you could have for amplitude loading, which is gray code. And the fidelities are really close to 100%, even using just 1 eigenvalue from the whole matrix. So I think this is a feature we would explore further, is to see how a better implementation of the controlled unitary for the reduced case, something like gray code, could even improve further these results. So finally, this graph is.
Rodrigo, yes? Sorry, last 30 seconds.
Okay, thank you. So this graph is for the 16x16 matrix. This just show you how the fidelities improve just by increasing the number of eigenvalues. So for 5 or 6 eigenvalues, you already get something close to 100%. And there is some difference between optimizing and non-optimizing the HHL. So you get different, of course, depths. So in conclusion, we found out mainly 2 things: that the results are sensitive to rescaling parameter k, so you can do a classical preprocessing to choose the optimal value of k. We also found out that by reducing the HHL, by choosing the most probable states, eigenvalues, I mean, you can improve a lot the depth of the circuit, the number of CX gates. And 2 steps further would be to do a gray code implementation of the multi-controlled unitaries to further optimize this reduced scheme. And what we did not do was consider reduced phase estimation by doing something similar to what was done in amplitude loading, which is reducing the number of controls whenever the control bits are the same. So that's it. Thank you for your time.
Thank you, Rodrigo. Yeah, I think it's a great project that you've done, and we have a few minutes for question. Yeah,
sure.
Ron, I see you raise your hand.
Yes. Thank you, Rodrigo. Very interesting and beautiful work. I'm Ron from Classiq. Not a question, but just a suggestion: keep an eye, and there is the lecture in 30 minutes about post-processing of QP results, and I think you will find it very interesting and relevant. And I welcome you. We can open, if you would like, a common Slack channel, and I will be happy to support in my free time, maybe if you would like to make some future work together with Simin and Christian. You will see their work in 30 minutes. So thank you.
Sure, thanks.
And we have time for 1 or 2 more questions. So any further questions from the audience? Yes, Amir.
I see that I'm unmuted. So also, it's not exactly a question. First, both Tomer and everyone that worked on this project, it looks really impressive. If I could suggest that you load the circuits and the code to some GitHub repository and make it public, I think it's really nice that people from anywhere from the community try to recreate this and maybe take it a bit further. I think it's a nice results, and this is a good way to maybe keep it alive a bit longer.
Yes, we want to finish the manuscript we started, and there we should put the GitLab link to the code.
Yeah. Okay. Very good. Thank you.
Thank you.
Any last question? Okay, great. So thank you for the HHL group. So now the next group, 27, the Q&A with Classiq. So you can share your screen, your presentation.
Okay, am I audible? Hello, am I audible?
Sorry?
Am I audible? Can you hear me?
Yeah, we can hear you.
Yes, okay, let me present. Is it visible now, the presentation?
Yes.
Yes, okay, let me start.
Perfect. So 10 minutes, we start.
Okay, good day to you, everyone. As a part of the Abuzer, as a part of the QCourse551-1 and the project 27 QNN algorithm implementation. And this project is managed by Tom Micheli, and the team members that I have also is Ashmit Gupta and Roman Ladam. So let's talk about this. Let's talk briefly about the project that we have done. So what does it do? We're just implementing a quantum neural network, but it's not totally like a quantum system. It's more like a classical thing incorporated with a quantum theme. And how are we going to do that? And that's like a basic schematic diagram. That's what we have done here. We're going to have a Fiji map that will be encoding our data into the quantum space and the answers that will be doing the data processing, and then they will have the measurement. So that's the more generalized of the quantum neural network. So what we have done here, since the problem that we are here solving is classifying a MNIST data set, and that will be recognizing a digit, a single digit, and that's what we'll be doing here. It's more like an image-related data. So this generalized diagram may have it needs to specifically in detail how to describe. So that's what we have done in here. So we have the classical data, and that has been processed. I mean the image pixel information, and that's been gone to quantum encoding, and the quantum entanglement that was with multi-qubit rotation and the C8 gate entanglement, and also the output processing and classification. Let's first talk about the data set that we have got. So initially we have got our data set for the MNIST digit from the PyTorch. However, this data set has it's like a raw data set. It's like a raw image, but we had to do some modification upon it because the data set contains from 0 to 9. Let's say it's 10 unique digit, but we have to disintegrate into just a two labeling or 2 digit. For example, we have taken 0 and 1 to binary classifying for it. So our goal has been set like that. we'll be doing a binary classification. So if it does work, then we will be advancing to the multi-digit classification. And that's the part we have just in here. We have just broken down the whole data set into a couple of files. There we have a folder that contains the multi-digit data set, and then another folder that says the binary digit data set. So now let's talk about what we have done. So we have got the data set prepared, but we need to do some pre-processing on the data set. That's a classical pre-processing, because we have, as you see, that this data set, it is a 22 by 22 and 28 by 28 pixel, but we cannot work on this on a quantum system because our quantum system does not have that much qubit to work on. So we have to scale it down into lesser qubit. So what we have done here, we have done some visualization and a statistical analysis on it, and decided that we can do some cropping on the border of the images and scale it down to a 24 by 24 pixel. And still it's like it's too many. So we have decided to downsampling it into 4 by 4 pixel. And how we're going to do that? We are creating a window and just averaging their value and putting a numerical on that pixel. So now we have 4 by 4 image, and let's say it's like a 16 pixel. Okay, and that's our data set that we'll be going to work on and pass it to our quantum circuit. So here comes our data being encoded into the quantum circuit. And how to have done it? We have decided to pick for 4 qubit to encode the 16 pixels. That's what our mentor recommended, to use the 4 qubits. So how did we just encode 16 pixel into 4 qubits? So we have decided to take 4 qubits along the horizontal line and encode it into 1 qubit. So here's the first, second, third, and fourth qubit. And how did we do that? We just we also additionally we have encoded the pixel intensity into the angle, and we have encoded it along the x and y and z axis rotation. So we have encoded it and put it into the quantum system. And we need to mix it up because the image pixel, they has to be correlated. They have some other relation among each other, among the neighboring pixel. So for this reason, we have done 2 qubit rotation, inverse rotation along 3 basic axes, z, y, and x axis. So we have tried to correlate every qubit along its neighbor qubit. So there's another part. It's just a normal, it's like a simplified control set operation along all the neighboring qubits, so that it's like a basic entanglement. The previous one was just for the correlation among the qubit pixels. And that shows the whole circuit that we have created, quantum circuit. And that's the first encoding that I said, and there's the mixing operation, and that's the set block here. And then the next things that comes is the post-processing, and I will ask Ashmi to take over the session.
Thanks, Asif. So here you can see we have got our measurement result. It is like, since our qubit circuit was of 4 qubits, so we have got a measurement from 0 to 16. But since this account it is in a dictionary, I just converted it into an array. So this first value is corresponding to the measurement count of 0, and so on. And then since we are using binary classification for 0 and 1, so I just trimmed it. So we are using now only 0th and first values of this array. So, and then to get the prediction probability, we just normalized this trimmed logics. And this is the post-processing step that we are doing before comparing the predictions and the actual label. Can you move to next slide? Yeah. So this is the simple neural network. It has only one quantum layer, and which contains the field like the circuit explained by Asif. And yeah, can you? Yeah, so here is the loss function training loop and testing loop. So the most important part in this is the training loop, because yeah, okay. So I think so in this training loop, what was happening is like we compare the prediction probability that we got and one hot encoded value of the actual label. So we take the Rmax of both and see if they are equal or not. If they are equal, then yeah, we have the correct prediction. If not, then not. We have the wrong prediction, and that's how we calculate the accuracy. Yeah, and same thing is done in this testing function also. Yeah, can we move forward? So here are the experiment, like results of our experiment. So in total, I ran around 6 experiments, out of which 4 experiments are relevant to us. So you can see when we were like doing the like classification for all 9, like all 10 digits, then our accuracy was very low, and you can see just a second. You can see our accuracy was around 9%, and like that was happening for all the experiment that we are running for all the labels of like 0 to 9, all labels. So then we decided to switch to only 2 labels, like binary labels 0 and 1, and then for like
Sorry,
around 10.
sorry,
Yeah.
we have 1 last minute.
Yeah, okay. So when we, for binary classification, we got around 50% of accuracy. And now our future plan is to just first increase this accuracy and then generalize it to all 10 labels. Yep. Can you move forward? Yeah. So some of the resources like that we used was, first was the quantum on-chip training with parameter shift and gradient pruning. And then we use obviously the Quentin guide in this Classiq documentation. And here's the repository to our code. And this is a weekly report to our project. Yeah. Thank you.
Very nice. Well done, Ashmit, and well done for being promptly on time. Yeah, so we have some time for questions from the audience. Are there any questions? Yes, Amir.
Okay, yeah, thank you again also, Tal and everyone on this project. It's really impressive. What are the, but if we had much more qubits, what would be kind of the scaling in the runtime? For, I don't know, if there were like 1,000 qubits, would the runtime be anywhere close to something reasonable?
First of all, like yeah. So first of all, like the like implementation that we are currently using, we won't be needing more than 4 qubits. But let's imagine if we have some more qubits, so the time will increase like around exponentially, I think, because it currently for per epoch and 32 size of batch 32, we are currently taking 5 minutes per epoch. So I think the size will increase exponentially. But the problem is when we increase the number of qubit, the accuracy will become low for like if we follow the current implementation, because as the number of qubit increases, the length of our like logits will increase, but we have to like we have just 9 classes. So for current implementation, we trim that to just 9 length. So if we take all 10 classes, then the 16 length was trimmed to 10. So you can see the value for the all position from 11 to 16 were discarded. So those measurement values will like contribute to the errors. So that's how if we increase the number of qubit and we follow the current implementation, then we will get low accuracy.
Okay, I understand. Thank you.
So we have time for maybe one more question from the audience. And if no one has a question, so I have a question, a comment. So any question from the audience? Okay, so I have one comment and one question. So in the encoding that you have, you encode you encode the data in four rotations. Yeah. You're doing like this. You're doing one after the other, but I think you're losing information here because the general rotation on the Bloch sphere is with 2 angles, and here you encode 4 angles after each other. So I think you have you lose information basically, and I think this might be a reason for the low accuracy of the test. So the common thing to do in this kind of scenario is to have 2 rotations, let's say Rx and Ry, to encode the data in 2 angles, and then to have some entangling layer like C0 or circular C0 layer, and then have another layer. So I think if you will change it in this way, you won't lose data, and then your model will be more accurate. And so I think this is if you want to continue work on the project, so that would be a good way. Also, I want to really thank you for the really nice blog post that you have done. So that's really nice and highly encouraged. And yeah, I see we have one question. So Bill.
Yes, just talking, this is a subject that I've done substantial work on outside. And I was saying, just to your point, you didn't, there's various image representations that can be used, FRQI, NEQR, that I think handle some of that information loss that you talked about that deal with not only the amplitude encoding, but also the preservation of the position of the pixel in the image. But yeah, I'll probably reach out to the 2 presenters just to get some more information. I'm highly interested in great work. Thank you.
Yeah. Like if you allow, can we like discuss this forward, Bill, through slide?
Definitely. Yes. Thank you.
Yeah. Thank you.
Okay, great. So thank you for group 27. Really nice work. I think we can move on to group 22 with the efficient sparse state preparation implementation.
Hello, am I audible?
Yeah.
Okay, so I'm sharing my screen. Okay, my screen is shared.
Yeah, but now the camera, I think, is off. Can you speak? Hello? Yeah, okay. Okay, and the 10 minutes, we start now.
So, hi everyone, this is Razinuddin, and today I am presenting the project 22 of QCourse551. Our mentor is Leo, and the project is the implementation of the sparse quantum state preparation algorithm. Okay, so we have 2 members with me. I have Shikhar.
Razin, sorry, Razin, can you speak more to the microphone? Yeah, perfect.
Okay, so this is the glimpse of the contents of this talk. So we are going through with some motivation and preliminaries and see the algorithm structure and the implementation of it in Classiq and in the Qiskit framework as well, and see the future prospects. Okay, so this project is all about the implementation of the results present in an efficient algorithm for sparse state preparation algorithm. So why quantum state preparation, as we saw in the previous HHL presentation, that we need some state preparation beforehand to solve the problem. So this required in many quantum routines. So the process of creating any initial quantum state known as the quantum state preparation. So in fact, so if we are using a gate library of 1 qubit gates and a C0 gates, so some of the general state of n qubit quantum system, it is known that it can be prepared with circuit of size with the computational complexity of size omega to n. But we have this sparsity. So in contrast to general states, many practical relevant states have the property that only a small proportion of the basis states have non-zero coefficient, and we call this the state with this property sparse, i.e. the well-known, the Bell states and the GHZs are the famous example. So Nielsen and sparsity can be leveraged to make state preparation more efficient than the preparation of general states. Is the intuition of the algorithm. So suppose we have a state phi, and the purpose of this algorithm is to provide a circuit C such that it encodes all the information present in phi in a way that whenever we apply this C to the zero state, the initialization of.
Sorry, Razin, we stopped hearing you. Razin?
Yeah,
now we hear you.
okay. So let me know where you lost me.
Just 10 seconds ago.
Okay. So this is the mathematical structure of our algorithm. So suppose we have the subset of an n-bit string with this with their coefficient of non-zero coefficient. So this is the classical description of a quantum state. So our motive is to find a sequence of elementary gates such that whenever we apply these gates sequence to the zero states, we create our desired state phi. But you can notice that this problem is actually equivalent to finding a circuit C prime such that the gates of the C prime in the inverse in the reverse order, so that when we apply C prime to to the phi state, we got 0 1, right? So so this algorithm doing in a reverse fashion. Okay, so this is the structure of the algorithm. So actually the main crux of this algorithm is choosing any two basis states which has most similar bits and applying this specific control unitary G such that these two basis state that it chooses previously combine into one but didn't affect any other basis state, and repeating this eventually leads to the state with only one basis state. And if this state is not in so we only left with one basis state. If this state is not in the 0 state, so we can apply the X gate and make it. So the implementation of this algorithm in Classiq. So the input form is, as we say that the input form is the classical description of quantum state. And what does it mean by this? That we have the input in the form of this list, which has the element which represent a basis and their corresponding probabilities. And after taking this input, the algorithm has the two parts. First one in the classical part. So the classical part provide all the classical information needed to proceed to the quantum part of the algorithm. So it accepts these basis state and probabilities. Just select any two merge pairs of these state using control operation and reduce the list iteratively. Along with this function record the history of all the gates like X, MCX and merging gates in form of lists and pass to the quantum part. So what quantum part does it from this list using this history of gates, that quantum part getting from the classical one, and since we know that the merging gate I show and the gate G, the X and MCX are the inverses of themselves. So applying them in the reverse order to all zero initialization actually give us the desired state preparation circuit. So these are the main two steps. So in this implementation, we use the auxiliary qubit as the representative of control qubits in each iteration. So and why we are doing this? So you can see that as an example, this is the states S, and when we put into the algorithm, it provides us this state and this circuit. So here you can see in the blue mark what in actually what we want to do. The blue one qubit is as the control, and we are targeted on the blue one to this. So the fourth one is control and the fifth one is the target. But as you can see, what we did is actually use some control qubit and then first flip this and controlling to this apply the control unitary. Why we are doing that? Because currently in Classiq, when the qubits occur in the gaps, like if the control qubits is 1 and 3, so there is no way in generally applying the control on 1 or 3. So whenever the control qubits occur with gaps. So generally we can't apply the multi-control in this sense in Classiq. So that this thing actually resolved the problem that whatever control qubits we got, we just take the auxiliary qubits so that we take our control qubit as without no gaps and apply the control unit. Okay, so after the implementation, what are our results and finding of this? So the advantage of this implementation is that it provides advantage in regards to the number of gate counts as compared to the currently available implementation of state preparation in Classiq. We do this implementation with two variants. Like first one, so the variants come from applying the gate G. So we call it the merging gate. So we did merging with the Classiq built-in unitaries and merging with the results of the paper. We use the elementary gates for quantum computations. And here are the results. So you can see on the left, these are the states. So don't take these are the only 4 states. They are just actually the representative of the actually the set of the states. So the state 1 and state 2 in the right hand side in the graph you can see. So the blue one is the actual right now Classiq implementation. So this is the existing method for in Classiq to prepare state, and it required these number of gates. So if our new methods, we did it with the elementary gates technique present in the paper and with the built-in Classiq unitaries. So you can say both provide the advantage, but the one with the built-in with the elementary gate technique provide us the more advantage than other. But and the another thing is to note whenever we leave the sparsity like in the state 3, you can see that in this scenario the current Classiq implementation provide a good result than than our implementation. And but the greater advantage is that if we have the more sparsity in the states like in the state 4, so you can see how large this difference be in our implementation and the current Classiq implementation. So this is the comparison within the Classiq technology. So we apply this algorithm in the Qiskit as well. So you can see this figure is just the current Classiq and the Qiskit. So you can see the here Qiskit does better. But when we do this new method in Qiskit with Qiskit built-in unitaries, so you can see that it doesn't provide a much advantage, although in the case of the more sparse state it provides. And when we compare it with the Qiskit and the Classiq unitaries method, so you can see that we start from this difference.
Razin, sorry, we have Razin, sorry, we have last minute, so
yeah. So you can see that in this figure we have we make this difference less, and you can see now in this implementation Qiskit and Classiq there are states which actually takes the same number of gates in both. In the future work, what we the comparison you are seeing is actually uses in our implementation. We use auxiliary qubit, so it means we our implementation require more number of that than the Classiq one right now. So we are now trying to implement without auxiliary qubit techniques in Classiq, and we are halfway around it as well. And after this, our main thing is to make this algorithm more efficient by using the another result from the paper quantum computations, which says that you need only the control X if you want to apply any control unitary. So that's it from our side. Thank you. Any questions? So this is the GitLab link of our rep.
Great. Thank you so much, Razin. Specifically for this project, this is a paper that I've seen a few months ago, and I was really interested in seeing how it can be implemented and to see it being implemented in Classiq, and the presentation was really good. So thank you. Any questions from the audience?
So we are also hopeful to get in touch with the Classiq team to actually implement it on the Classiq, hopefully. If
Great. So we can be in touch in this regard. This is really interesting. Any questions from the audience? Okay, so I have one question. So in slide 15, you said something that you cannot control the gate specifically with Classiq. I wasn't sure what you were referring to.
yeah, so let's consider the scenario in which we have to apply a control unitary. This control unitary based on the qubit 1 and 4. So since there is a gap between the control bits, because the first one is 1 and the other one is 4. So right now we can implement this unitary for a specific example, but in generally we can't right now in Classiq. So we can if there is no gap. That's why we use this technique. Say okay, make this auxiliary qubit the control one, and for the other one make another auxiliary qubit to the control one. And since both the auxiliaries are now are without the gaps, so we can easily apply generally this control qubit controlling on these two auxiliaries.
Okay, I see. I have a question. Have you worked with the old Classiq language or with the new Classiq?
No. As we already said that this one is for the new one.
I see. So I'm not sure why you can't do it. We can maybe discuss it later because you absolutely can do it with Classiq. You can use any control on any gates and any qubits that you want to be control and target. And you can join the two quantum bits to one quantum array and then use them as a control. So you have many options.
Yes, we can do in a splitting and joining technique, but it has its drawbacks as well. So I tried that, and I will discuss this with Max Vetan as well. So yeah, there is a technique, but it also has some restrictions in applied in generally. So for specific cases, it works really fine. But in the the basic problem we are getting is the port name things. So whenever you apply any name to one port, you can't use it again and again. So at every time you have to give a new name to this port and use the splitting and joining technique. So that's the crux of the problem we are facing right now.
Okay, I see. I'm not sure if we understood, but I would love to continue and hear about it more. So we'll be in touch. Great work. So thank you. Yeah, and I think we can move to the next presenter, which is project 32 with the curve-fitted quantum phase estimation.
Okay, thank you. I'll present my screen now. Sure. Can everyone see my screen?
Yeah, perfect. So we can 10 minutes start now.
Okay, thank you. I'm Seamin. I'm from the curve-fitted QPE group, and my group mate is Christian, and our mentor is Ron. So here's an outline of my presentation. So we'll start with the background first. This is the usual QPE circuit that is the traditional QPE circuit. But the issue with this QPE circuit is that generally there is the issue of spectral leakage, where this recording qubit cannot capture the full precision of the phase that's being estimated. So for example, for theta 1/3, that's just impossible, for example, or otherwise we would not know what is the number of qubits that are necessary for this to capture full precision, even if it were possible. So firstly, this is how we implemented the circuit using Classiq. Now our method is basically a variant of QPE, which utilizes the QPE circuit, and we aim to mitigate the spectral leakage issue. By spectral leakage, this is another diagram which shows it accurately. Usually, in the QPE, we would just take this one with the highest precision, but with our method, we can achieve a higher precision using curve fitting. Our method would thus extend these results to like a higher precision, while dealing with the constraint of a limited number of qubits in this NISQ-Era. So our method basically involves first deriving this the probability of observing a certain state Y. This is the usual probability, but we also derived in our paper. And we can curve fit this probability equation onto the results of the QPE. In this case, the QPE is executed for 2048 shots. Usually in the traditional case, we would just take Y equals to 3/8 to get our theta, although that the actual theta is 1/3. In our method, we would instead we get the estimated theta as being the highest point, which is far more accurate. This is our function in pseudocode. Basically, we call it curve-fitted QPE, which takes a quantum program. This quantum program is as defined earlier using Classiq. And first we have this function called getCounts, which executes the quantum programs and returns the Y and the shots for each Y. We can then curve fit it using this fitting curve parameters function that we also wrote up. And thus it will return this estimated theta using the SciPy curve fit method. This is our function in the full Python code. We also did mathematical analysis on our method. So basically, we are interested in finding the Cramer-Rao lower bound because it can give us information on the mean squared error. In order to find this Cramer-Rao lower bound, we first need to find the Fisher information. And this Fisher information can be found based on this probability of observing Y. We can find it through this formula here. And Christian has derived this equation for the Fisher information with respect to theta. Plotting this Fisher information equation with respect to this theta, we can then see that it's basically a constant value. Even in this right-hand side case, we see that it's actually the same value, so these peaks don't really mean much. So we can find the Fisher information value for each case of M. M is basically 2 to the power of qubit of recording qubits. So this is the individual Fisher information for each individual shot. So in order to find the total Fisher information, we have to multiply it by the number of shots here. So basically, the Cramer-Rao lower bound states that the minimum mean square error has to be more than or equals to 1 over this Fisher information. Oh no, okay. Sorry, it was not changing. Here are our results. So firstly, we can check this order of error resolution. When our RMSE is plotted against the num shots, we can see that our experimental results, the colored ones here, follow a 1 over square root n order. In the case against the depth or the recording length, this is the same as the M previously. It follows a 1 over n order of resolution. This means that our method basically follows the Heisenberg limit of 1 over square root k times n, where k is the num shots in this first case, and n is the depth or the recording length in the second case. This Heisenberg limit is, of course, basically the quantum advantage case compared to the standard quantum limit. Of course, however, that our method requires a large number of num shots, so it has to be admitted that it will predominantly follow a 1 over square root k. So it's basically assumed for that portion. We can compare our results to the CRLB, which we previously derived, and we see that actually we achieve very good results. It basically lies practically on the CRLB, which means we can achieve this minimum error case. However, this is as long as the number of shots is at least more than 4,000. As you can see here, the ones that are less than 4,000, there's all these peaks and garbage here, basically. Yeah, we can also see this more clearly in this graph, where it's plotted against basically like the Heisenberg limit resolution. And we can see that it follows this Heisenberg limit and it lies on the CRLB. The CRLB is this black line over here, as long as the number of shots is at least 4,000. Which 4,000 isn't actually that much compared to like 2,048, which is quite a common number to use. So this is like our discussion. Our order of error resolution of 1 over square root k times n, predominantly order 1 over square root k, is comparable to very front-running methods in this field, such as the VQE, the variational quantum eigensolver, and another method like the maximum likelihood amplitude estimation. Our method can extend this QP precision, as we have previously discussed, and it can be used as like a developmental tool. For example, if we want, given this NISQ-Era, there's only a certain precision we can achieve using the limited number of qubits. And therefore, with our method, we can achieve a higher precision with the QPE method. And this can be as part of a larger algorithm to test out this larger algorithm. Some further work is that we can compare with alternatives, and another method we did look at but haven't fully explored is this multiple eigenvalue estimation, where more than one eigenvalue is involved. For this comparison with alternatives, one thing that I've been reading up about is that our method can allow for parallel execution of the quantum circuits, which means that although we would require the same order of resources compared to variational quantum eigensolver or the best classical methods, we could technically have a speed up in that sense because we can parallelize the execution, which methods like the VQE or the classical MC simulation, which is one of the best classical methods, all of these require sequential executions. So yeah, that's our work. Thank you, and we welcome any inquiries or comments from the audience. And this is our GitLab.
Thank you very much for the nice presentation. Any questions from the audience? So I can start with the question. So you showed one graph over there that the x-axis was the square root of the number of shots times the depth of the circuit. So yeah, so why this is the correct metric to assess your algorithm basically?
It's basically based on the earlier result of this one, where it follows basically 1 over square of n, which is 1 over square of num shots, and 1 over depth. So this is basically 1 over square root num shots times 1 over depth would be just now that square root. Yeah. But it's also basically the Heisenberg limit here, 1 over k and square root k, and yes. But basically we can see that it's like linear to this, it's a linear graph. So it basically shows that yes, it's following this Heisenberg limit. And furthermore, we can also compare it to a CRLB in this case, because we can see all of these lines, all of these points lie very well on the CRLB line over here, as long as the num shot is at least 4,000. Okay.
I see, thank you. And for the implementation of the quantum phase estimation, did you use the built-in QPE of Classiq, or you derived your own QPE?
Oh, I'm so sorry. Yeah, we did basically use the Classiq one, but I used a phase gate so that we can check the error, of course.
Okay, I see. Thank you. Any further question? Okay, thank you very much. And we have two more groups of project 32 to present, I think. Or one more group, no, two more groups. So thank you. And the next presentation is quantum backtracking for CSP problems. So we could, yeah, David, can you share your screen?
All right, can you see my now?
Yeah, we see the desktop. We don't see the presentation.
Oh, it's true. That work right now?
Yeah. Perfect.
Okay, thank you. I want to thank my mentors and supervisors helped me during the journey. And we try to solve the problem of the constraint satisfaction problem with the quantum backtracking. And that's a new module you're going to develop. So the problem basically the growth algorithm really good for the speed up in the non-structured problems. But the thing here in structured problem, there's certain trees is unbalanced. So you don't need to search everything possible choice. So the way we figure out like you can speed up the with the structures with the backtracking approach and quantum walks. So we try to figure out how to develop the backtracking algorithm based on Classiq platforms. So the first one is reference. Basically gives theoretically background how do you speed up. And this idea how to compare the performance. So growers need to have a square root of the total possible vertices. But real life here, there's only a few vertices need to travel that. So the quantum backtracking will really good on performance if t is much less than the d to the power n. So there's certain challenges here because we don't have all the information about how to implement, especially how to do the diffusion operators over local trees. So that's a challenge. So we try to overcome challenge. Also, we have problem with the teams. So we're only one left here. So actually, what happened there? We're going to try to use some open source program performance modules. Then later on, we implement in the Classiq. So here's the way how to describe CSP. So basically, have variables to the n variables. You have a value from 0 to d minus 1, and so you create a trees from root the different choices, and you try to search the trees and try to figure out do you have a solution for the predicate. If found it, you say yes, you stop. If not, you continue. So here for Classiq backtracking algorithm here, you start from root and you check the predicate. If false or it's completely stop, otherwise heuristically pick up one values and modify values and do the basic recursively try to figure out solution. Right? You look at trees. And here the way for the quantum backtracking is a little bit different. So we try to figure out how to do that. You're not going to do that recursively. So basically you create the whole operators. And after operator, you're going to try to figure out is operator, try to figure out is the solution there by use the OPE. So there are different operators. One is basically over all the even distance from tree root. Another RB is the vertex over all the R distance from root tree. So you have two different choices. If the X found it, you basically your diffusion operator just identity. Otherwise, you do this similar to the growth algorithms, pretty much similar. One I minus something. So here is different way how to figure out the operators over different indices. And the B is kind of over the R vertex, so you kind of do a little bit different. So the way how to figure out a solution will be you try to figure out use the phase estimation, right? You do the multiple times, just like the group algorithm here, right? So here do certain time here, eventually either find it or reject it. So the minimum will be 3K divided by 8. So it's really there's a fixed number you're gonna need to do that. So that's make sure more efficient than the growers. Because growers have to look at all the possible choices here. So you only look at certain thing here, and also use the phase estimations. So that's different choice here. And the way how you find solution, we basically do from root, you try is this detected? If detect continuous, if not, go deep subtrees. That's how I found the solutions. And the way we solve problem here, because we have some difficult time try to implement in the collective first time. So we have a really ambitious plan how to solve the Sudoku. That's really hard, right? Because Sudoku really a lot of the space is so high, right? 4x4 Sudoku. So we try to figure out how to do that. So I'm use Chris for now and solve the problem. And later on, we're going to use create a Classiq backtracking trees modules and try to solve general SAT problem. So basically the SAT is basically a satisfaction problem here. The Sudoku is part of that problem here. So here, the thing here, we solve the Sudoku 4x4. If you look at all the tutorial IBM Qiskit, they only solve 2x2. So everyone shows Sudoku solution they give picture of 9 by 9, but they only solve 2 by 2. So actually we solve 4 by 4 with our simulators. So here is the way implement, right? We have this 0 to 3 and -1 means it's not founded, right? So 4 by 4 means cross the vertex, cross the rows should be 1 to 4, and also the 4 squares, 2 by 2 squares also have 0 to 1 to 4. It should be uniquely identified. And here is the way we try to figure out how to trade off, right? You either have 40 qubits, you're going to have a long length. If you have a short length, but if you have 30 qubits, you have a really high depth, right? How many depths you're going to solve there? So that's a different choice here, right? So imagine we got to figure out you can have 30 qubits, and there'll be longer 30 qubit long depths here. So, and we use the Classiq to try to synthesize the solution here, how many depths you're going to have, and also we use from the Classiq, we use IBM MPS run the solution here, right? So we solve the problem, and you use IBM MPS. We found a solution here. And the second part here, we basically how do you implement in the QBT in the Classiq. So we did that. We didn't complete yet. So here is something make progress. So we did for the growth search, we're going to compare them. Then we did the QPE, right? How do you estimate the phase, the quantum phase estimation? So we did that in the Classiq. Then last part, we're going to try to implement the IRB, that's the diffusers, also in the Classiq. We almost done, but we're not done yet. So basically, next step here, we try to implement the Classiq model quantum backtracking module fully, and also write a block, and also finish up the how to use Classiq QBT solve the SAT problem. So that's it. So we have a GitHub on it also.
Thank you, David. Thank you very much for the presentation. Any questions from the audience? So I can start with a question or a comment. So I think specifically for this kind of project, to implement all the diffuser operators and to add the different states together. So I really think that now in the last, let's say, 2 months or 1.5 months, the new QMod and the new Classiq language, it's really a substantial improvement for implementing these kinds of things. So with the old SDK, basically, it was really, really hard to implement it. Now with the new SDK, I can share with you some examples later on that I prepared last week. Implementing a diffuser operator is really intuitive and straightforward, and I think this is the significant building block for your implementation, and maybe also a linear combination of unitaries that you might need to implement. And both two are really convenient. Now you can do it exactly what you want with Classiq. So yeah, I'm really looking forward to see the next steps and the next implementation with the new QMod, and I'm happy to help with any further tasks that are needed for this kind of progress.
All right, thank you.
Great. So if we have any, yeah. So Saif, I can see you raising the hand, so please go ahead.
Yeah, thanks. You hear me, right?
Yeah.
Okay. Just one small question. About after the solution, all the qubits need to be reset again. You do the measurement to find your solution, right?
Yes.
Okay, thanks.
Yeah, so basically use QPE you found solution here. So that's the whole idea here. You got different operators, then you just run through the QPE. They found solution here. You measure them. I mean, the whole idea is diffuse operators and also the QPE. That's the whole idea.
They're saying weak measurement could play some role here, or?
I'm not sure what you mean. I mean, we had a operator, then use QPE, solve the problem.
Okay, thanks.
Okay, so if we don't have any further questions, so thank you very much, David, and thank you for continuing the project and with all the hurdles we had along the way. And the last group for this first session is group 23 with the quantum search for Bitcoin mining. So please share the screen.
Edan, they didn't contact me.
Yeah.
Somebody is here now. Okay, good.
Okay, yeah. So hi, hello everyone. So our project is quantum search for Bitcoin mining. Let's start. So what Bitcoin mining is? I'll just explain it in a brief way. So what Bitcoin mining is, it's a process through which new Bitcoins are added into the public ledger. What public ledger is? A blockchain actually. Bitcoin mining is a process through which new Bitcoins are created and added into blockchain. As of January 2024, there are some approximately 90 million Bitcoins, and of total 21 million Bitcoins they have been mined. But this Bitcoin mining is a huge market and has a capital of almost $500 million per year, along with a CAGR of approximately 12.90%. You mean this is a huge amount of money that is being produced by Bitcoin mining industry, and how we can use this for our advantage. So this is our projects. So let's start with what blockchain is and what hashing is. A blockchain is a decentralized network. You have heard about that, blockchain, Web3, and all this thing. What blockchain is actually, there are various computers on all over the web. So these are simultaneously working in order to create this blockchain. But the whole thing is comes down to security. How much secure is this? To keep this thing secure, there's a process called hashing, through which a proof of work is been registered and digital signatures are verified. And then later on, these signatures are verified with this solving this complex mathematical problem. And thus, the new blockchain is added if the signatures are verified by the hashing process. Let's go on to what hashing algorithms are. The most important hashing algorithm right now in Bitcoin mining is SHA-256 hashing algorithm. It takes an input of 2 to the power 64 bits and gives us 256 digest. Actually, what happens in Bitcoin mining is the actual input is hash double in order to make it more complex. So we tried a similar algorithm for our project, that is SHA-1 initially, but due to its complexity, we later on shifted to MD5 algorithm, which was much simpler. Now let's come to how Bitcoins are mined actually. So right now there is no any algorithm that would be able to mine Bitcoins. We use a brute force approach, that we use every possible nonce value that could be used in order to find a hash value that at certain difficulty level. That is, it has some kind of prefix zeros. That is a difficulty level determined by the basically the system that is present in Bitcoin mining. You can see in the next slide that there is a slide thing that in the first year you can see that there are 3 zeros, and it took approximately to solve this by brute force algorithm. It took 0.4 seconds. For 3 zeros, it took approximately 6 seconds, and for 5 zeros, it took 23 seconds. You can think about it. It is increasing exponentially, and in today's date, there are almost 35 zeros required. So it takes approximately an hour or so in order to verify that transaction. Now, how quantum algorithms comes into play? So the thing is, Grover search algorithm is an algorithm in order to find unstructured unstructured database actually. And Bitcoin, the hash and nonce values are also unstructured. They are not in any structure. It could be a 1, 2, or 50, 60. That could be any value. And it takes approximately 256 possible values in order to. So this is a huge number actually. And this is a very high energy intensive state. It requires there are various application specific integrated chips developed for this purpose actually. But we know that Grover search algorithm takes gives us a quadratic speedup. So we will be able to possible to find the hashes with a limit of 2 to the power 128. But the problem is we'll require approximately 10,000 logical qubits for SHA-256 algorithm. So our project was to show that this is possible. Actually, with this, we'll be able to solve the query complexity problem. We'll be able to get advantage in query complexity. So what we did is we reduced the problem into a simpler version of hashing algorithm, that is MD5 algorithm. and we reduce this hashing algorithm into a simpler method, into a very simple, basically a mixer function that is present in the MD5 algorithm. And we use this MD5 algorithm in order to create a mixer function, and then use this mixer function to create a Grover search algorithm, which will be able to solve it using Classiq SDK. I think now next on, Marvin can tell what actually we implemented. Marvin, you can continue. Hello. Hello. Marvin, you there? He can't unmute right now, I think.
Okay, I'm unmuted.
Yeah.
Thank you. Okay.
Yeah.
Okay, advice, I can continue. Okay, so you share the screen well. Okay.
Yep.
Okay, so as advice has explained, I mean, as Adut has explained, we want to find X value which is going to correspond to at least difficulty 1, because we only have hexadecimal values, about 8-bit inputs. And so you only have around 96 ASCII characters to play with. ASCII characters are like characters on a keyboard, A, B, C, D, capital A. And if you crank this number using brute force in the simplified MD5, you'll get 4 hexadecimal outputs that return hex values with difficulty 1. And that is values with 0x01, 0x0, 2, 0x03, up to 0x0f. So out of these 16, you can get 4 values of that nature. Yeah. Okay, let's proceed. Okay, so when we move away from the classical way of doing the MD5, we now have to encode the simplified MD5 using the Classiq SDK, Classiq Python SDK, and the first step is to build the arithmetic oracle. And this arithmetic oracle, because it's not having any inputs, it's like an oracle which is just built in the system. You've not yet defined the inputs for the oracle. It's going to return 100% 0, 0, zeros, which is like difficulty 2, because you have 0x00, 0. You have the double 0. And this is something you can see, maybe just to show you the arithmetic oracle. You can share the arithmetic oracle. Just show you the code that we actually did this. We didn't just maybe do it in the SDK. I mean, do it in the platform and then just put something in the PowerPoint. We have the code. Our time will not allow us to run it, but yeah, if you zoom in this, you are going to see that there is arithmetic oracle here. So you code this, and then you want to find the value B, the ASCII character. You want to get the hash, the simplified MD5 8-bit hash of B. Okay, let's go back. But however, since you don't yet have any inputs, you can only get this graph. Let's go to the next slide. Yeah, so this is the graph. If you zoom in this graph as well, our system took only 19 bits, so it was actually optimal, because our maximum number of qubits that we should have used should have been 25. Yeah, but then we managed to use 19, so you can see 0x19, 0x power 17, sorry. And then you have these 2 extras, which means all the qubits are returning zeros because you don't have any inputs to the system. Okay, so now you need to build a graph operator for the simplified MD5. So if you add the Hadamard transform to the target qubits, which target qubits are the 2-bit inputs? There'll be 2-bit inputs encoding for A, B, C, and D. You can then mod a graph operator for that. A graph operator which is going to be containing an arithmetic oracle and a Grover oracle. Okay? And so a Grover search of the ASCII character B will actually return something. We could first see how let's just see how the code looks. Let's first see the code, just to see the Hadamard transform that you have to add to the, so the Hadamard transform in this Grover's, you can scroll, Yeah, so the Hadamard transform is down here. You have model.hadamard transform. Yeah, and then the parameters are here, where you have model.graph operator in orange. Then you have A, B, C, D. Yeah, you're modeling those inputs on the arithmetic oracle to form a graph operator. Okay.
So Marvin, we have last minute for the presentation.
Last minute. Okay, let me use it. Let me use it well. I think. Sorry, I first went off. But just show our dude can just share the picture for the letter B, and then there was also a picture for a picture for the code, the circuit. Sorry, I think you saw it somewhere. We can just go to, yeah, this is a circuit. Just in the end notes, just to say the last word on what we could have done better, you can just go to the last point. So I think what we could have done better, I discovered that we can actually model the SHA-256 using one run of it uses around 1,040 qubits. I wrote some article about it, but there's some Bitcoiner did. He was hashing using a pencil. And if we are given more time, we could have explored that and used the SHA-256 itself within the Classiq code. Thank you. And yeah, that's our presentation.
Great, thank you very much. Great work, and I think this topic is also could resonate really well beyond the quantum computing community. So if you would write a blog post or something like this, I think it can really resonate outside. So that's a great work. Any questions from the audience?
I think I'll actually take it on. I'll try to write another blog post, a blog post of our presentation here, because I sort of write blogs, yeah, technology stories. Yeah.
That would be perfect.
Yeah.
Any questions for the group?
Maybe, I don't know if we shall share later something I didn't present, but you can also output in the Python Era EPL and play with the code without going into the Classiq platform. It's provided by the Classiq SDK. Yeah. So it's something we also did in the code we have in our deliverables. Yeah.
Great. Great. I think again, like a blog post for this kind of topic, I think it can resonate really nice. Yeah. Okay.
Actually, my next blog will be, I think, on this, how we did something to try and model this hashing. Yeah.
Okay. Yeah. Great. Okay, and we have a very so thank you for group 23, and we have a very nice surprise with additional group to present. So that's really nice. So Crystal and Vanesh, welcome, and please share the screen.
Thank you so much for letting us present. Yeah, things have been a bit wild for me personally over the past few weeks. So let me minimize this. Oops. Nice. And shoot. Oops, wrong one. Slideshow.
Right. So we are starting the 10 minutes, and there will be the last group for the first session before the break. So
thank you so
ahead.
much. Okay, so hi, and thank you for coming to our final presentation today for our group Quantum Backtracking for Sudoku. So we're Team VK, which consists of Vansh and myself, and we're mentored by Eden. And so the early goals for our project, our initial goals were to read the assigned background papers, decide what sort of problem application we wanted to focus on, and understand this marked vertex mechanism, which David spoke about, which is the focus of the speed up for the initial Montanaro paper, and understanding classical backtracking in the primary papers. So our next goal was to implement quantum backtracking according to the paper using Classiq, and to evaluate our implementation using some sort of benchmarking, which was more of a stretch goal. So for our background, we were assigned these two papers, the main one, which is by Montanaro, which is at quantum walk speed up of backtracking algorithms, and the Martial paper on practical implementation. And so we started by completing the mandatory bootcamp, which you all did, and then learning about the Python SDK. So some of our initial problems to solve were that there was no open code base from either of the papers. So, how do we navigate this? And it meant we had to start from scratch in understanding the paper and trying to implement the intent of the authors. So our next question was, how much will the papers we have help us to understand our algorithm? And also our project is a new application of the algorithm on a specific problem that hadn't yet been solved. So what problem would we like to solve? Considering things like the traveling salesman and the four-color theorem problem were discussed in the original paper, and they were already covered in previous papers. So also, given that we have no current implementation to evaluate against, how do we evaluate our implemented algorithm and check that it's a correct implementation? And finally, what does speed up look like? So we agreed early on to solve Sudoku. And Sudoku in one of those ways becomes challenging because by changing the number of hints, you get different results. So then what does a quantum versus classical implementation look like? Are they similar in implementation or significantly difficult? And back then we had no idea. So our timeline was something like this, where we spent quite a bit of time after the Classiq bootcamp reading and trying out the first method, implementing the classical backtracking and benchmarking that. And then we switched to our second method, which is a quantum implementation based on mentorship from Eden. So you'll see that we have a first method here and a second method. And so for our classical methods, we had them onto in our paper, which showed this predicate and a heuristic such that we get some kind of an assignment that either leads to a solution or recurses until it finds one, or doesn't find that the solution exists. So Vansh wrote this backtracking code for the initial Sudoku problem where a file is parsed. So this file is here, and we have a number of hints, which are identified by these dots. So we have the hints, which are numbers, and then these dots, which are the missing values. And we have the Sudoku driver, which finds solutions and prints them out. And this is the code for that, the code base, which is open sourced. And then we benchmark the code using a number of tools. So Vansh was able to show that actually the number of hints here, you can see some of the benchmarking code here matters. So what we see is that the time to find a solution decreases significantly as the number of clues increases. So onto the quantum methods. If we scour the internet, we see a couple Sudoku implementations in tools like Qiskit, for example, but they all use pure Grover search, which is a lot easier to implement and which is not what we want. So this Medium post by Jessa came out actually 4 days ago, and it's a good example, but he says in his post that since current quantum computers are very limited machines, we cannot solve a real 9x9 Sudoku puzzle. So our toy example uses 2x2, which David also spoke about. So everybody uses this 2x2 matrix. So the method that we were looking at uses an optimized specific marked vertex and quantum speedup that should get us better performance. So we should be able to get a little bit better than that 2x2 performance. So initially, we tried to find an open source implementation associated with the paper as a starting point, but we couldn't find any. And then also using the paper to implement the quantum algorithm proved to be tricky because the paper leaves out a lot of information needed to do this. So we tried to find an equivalent method for implementing the quantum algorithm. And this is where really what we spent the bulk of our time. So eventually, Eden met with us and identified an approach that we could use that consisted of 3 steps in Classiq. So we create this state operator psi, we implement amplitude amplification, and then we use 3, which is the linear combination of unitaries or LCA. So this goes into the things we learned. And with that, I can bring in Vansh to talk about some of the methods we use, which are in our code base, which are the state operator, amplitude amplification. Yeah.
Hey, thank you. Can you go back to the state preparation slide?
Sure.
And I can maybe start from there. Yeah. So essentially what we discussed with Eden, our mentor, was that the idea of state preparation was imagine a classical Sudoku board and imagine putting all of that on a singular quantum state where the fixed values represent the clues that you predefine on your code. And that's what most of our state bounds were. So as you can see, one of the states which was one of our clue to be 3 on a 2x2 board. So you represent one of the boxes by 3 and all the others are just fixed value zeros. Zeros means nothing. And Crystal, next slide. Yeah, and then keep going. This is just more of that state preparation. And then the idea is then we want to use amplitude amplification, but and you can use Grover's pre-built algorithm in Classiq for that. But one of the key points is it's not the same state that you're amplifying over because Grover amplifies over the superposition of all possible states. So we just wrote a small function that takes the required superposition that we want and then applies the Grover operator to that. And that amplifies the amplitude of all the solutions that we want to check for. After that comes the point where we check for constraints. So Sudoku has some inbuilt constraints like, you can't have 2 same elements in the row and a column and all those. We check for those. And then we want to apply the linear unitaries, which Crystal can talk about.
Okay, so that goes on to our future work. So we want to complete the implementation. So basically LC is our last step. So that's actually particularly challenging, but it will allow us primarily to instead of using products for a DFX operator, to use O pluses, so sums. And this is something that we plan to complete and write up our results. And we plan to open source our code. So this would, between David and ourselves, probably be some of the first implementations for these kinds of problems, so you can get a better result for Sudoku. So just to conclude, some of the things that we learned in this project are the importance of open sourcing code in research, which is still a huge problem. So rather than starting from scratch, it would have been nice to have some baseline so that we could have been able to compare a specific implementation for Sudoku with the author's original implementation and check for reproducibility. So secondly, our mentor's domain knowledge in quantum implementation led to a significantly different path compared to our original implementation. So we spent a fair amount of time trying to figure out how we could get this marked for text implementation. And quite frankly, I didn't know about amplitude amplification or LCU or the psi operator. So having Eden tell us and work through with us that this is something that we could use was tremendously helpful. And finally, the application of our problem affects resources. So Sudoku itself is an exhaustive problem. So can we optimize the number of qubits used when our final implementation is up and running? And this is something, given I spent a fair amount of time working with SAT solvers, once we get the implementation, maybe we could tweak our constraints. So with that, we looked at a lot of resources because, as you said, there was just not any information out there. And thank you to everyone and to our mentor, Eden. And we can take any questions at this time.
Thank you, Krista, and thank you, Vanesh. So I think specifically the quantum backtracking project by you guys and by David, it's a great example for high-level functional design in terms of there are concrete functional building blocks that when we put them together, it's exactly implementing the algorithm we want. So for this, the example here is to create a state preparation, which is a functional building block, and then to do amplitude amplification, which is another building block, and then to do linear combination of unitaries. And so I think it's a great example of how we can combine functional building blocks in order to create our algorithm. And I'm looking forward to seeing the everything coming together with the implementation. Yeah, any questions from the audience? Okay, great. So if anyone come up with a question, so feel free to write it in the chat or in the coming time during the break. And yeah, if not, so we can conclude the first session. So well done to all of you guys. So both the presentations for this first half were like really good, and everyone went really on time. So we even finished 5 minutes before with one additional group. So well done, guys. And yeah, we'll have now a 30 minutes break, and on 6:45 Israel time, and I think Latvia time as well, we'll continue with the next group, which is group 33, implementing quantum arithmetics. So we'll start in 6:35 with this group. So this group, please come 2 minutes before, and then we can test your screen sharing. Otherwise, if anyone has any question for any group, we have now time. We can keep this session open. Yeah, and thank you for all the groups so far. I'm looking forward for the next half. Hi, everyone. So welcome back to the second part of the final presentations of the Q course. We have 6 more projects to go. So we can continue with project 33, implementing quantum arithmetics. Please go ahead. We're starting the time.
Hello, everyone. This is Thomas Pilikas from Group Alpha Beta of Project 33, designing native quantum arithmetic language. Our mentor is Madam Hawks. Our primary objective is the development of a compiler tailored specifically for arithmetic expressions. This involves the translation of arithmetic expressions into executable description achieved through the utilization of Classiq's lower-level functions by integrating it with Python SDK. Throughout the development process, we delve into the intricacies of language semantics and explore avenues for optimizations to enhance the overall efficiency of our implementation. Let us be a little more specific. We can split the translation of an arithmetical expression to a quantum program into 3 levels. The high level is the arithmetical expression per se, written as a Python string. Then there's the middle level, which is the description of the arithmetical expression as Classiq's lower level functions. Finally, it is the translation of this Classiq script into quantum circuit to be executed by a quantum computer or a simulator. We're mainly interested in the first translation, that is from high level to mid level. We want to construct an arithmetic function such as the arithmetic function in Classiq's library, compare it with it, and probably merge the 2 functions in an optimal one. In order to do so, we split the project into 2 steps. Our first step had to do with calculating some characteristics for each sub-expression. First of all, we calculated the arithmetical expressions domain. As domain of a variable, we assumed only interval domains. And then we performed usual interval arithmetic in order to recursively find the domain of each sub-expression and the final expression. By this domain, we could determine whether a variable or a sub-expression is signed or unsigned, and then an expression is signed explicitly if and only if its domain contains negative values, or it contains a signed sub-expression. By this sign, we can then determine whether the number of qubits required for the representation of the variable of the sub-expression. For unsigned variables, we use the usual binary bit representation, and for signed ones, we use the 2's complement method. And then by that, we recursively define the number of qubits via the rules here in this part of the screen. And when we had to jump from unsigned sub-expressions into a signed one, we should probably introduce some additional qubits. We recursively evaluate if expression by constructing its abstract syntax tree using the abstract syntax tree library of Python, which was returning something like this. And the code of our first step is here. The details doesn't matter so much, but what we have is that we give as input the quantum variables and their corresponding domain and the arithmetical expression, and this function was calculating exactly the domain, the number of qubits, and whether they are signed or unsigned. As a second step, it was exactly to construct the arithmetic function. We worked on creating the model per se using the Classiq built-in functions. We tried to create the model through the recursive evaluation of the abstract syntax tree, and let me give an example of how this was done. We start from the leftmost leaf, which is in this example A. We prepared the corresponding state. We calculated the characteristics of step 1, for instance, if it's signed and the number of qubits, so we could prepare the corresponding quantum register. We did that also for the other variable of the binary operator, and we could calculate the addition. Then recursively, we calculated the domain, the number of qubits, and whether it's signed or unsigned, and define the corresponding quantum register. We did the same for the rest of the abstract syntax tree, and we ended up implementing the arithmetical expression required. But there were some problems aroused. Those problems have to do with multiple occurrences of the same variable. For instance, let's have A equal to 1 and B be on superposition of 2 and 3 with equal probabilities. Then what is the value of A plus B plus B? Well, in our initial implementation, for each occurrence of some quantum variable, we prepared some new auxiliary qubits. So we prepared some auxiliary qubits here for B and some new here. This, first of all, is not optimal according to width, but also return false results because B here could be equal to 2 and 3, and here equal to 2 and 3, but independent between those two B's. So this secret actually returns 5, 6, and 7, while it should return only 5 and 7 and 7. In order to resolve, we keep track of each quantum variable in the whole width of the circuit and probably use the corresponding wire for next operations. For instance, here we keep a wire for B and use it for the next addition. And we can see that the results here are the expected one, 5 and 7 with equal probabilities. But what for expressions as A plus A, or in general for expressions in which one of their maximal percentage binary operators contain 2 times the same operand? In fact, Classiq's built-in arithmetic function fails in such expressions. It returns repeated variables in the beginning of an arithmetical expression are not allowed. And this happens because we actually have just 1 wire for A, while we should have 2 as addition is a binary operator. We try to resolve this by trying to copy A, but of course this is not possible due to no-cloning theorem. So instead, we used some auxiliary qubits which were prepared using control X gates for each qubit of the quantum variable A. Here is the implementation. So we prepared A, and then we took some auxiliary qubits and prepared them using those control X gates. And we can see that the result was as expected, 1 plus 1 is equal to 2. But those auxiliary qubits are entangled with the qubits of the quantum variable, and we should untangle them. This falls into the general problem of uncomputation, which states that we should uncompute intermediate results because entangled states might collapse each other concerning problems to the rest of the model, but also for circuits with optimization. As quantum operators are reversible, intermediate results can be uncomputed by performing the reverse operations or the gates in the reverse order. Okay, now an uncomputation strategy is the order that the computation and computation operators are performed. And according to this strategy, there might be a trade-off between the circuit's width and the circuit's depth. The easier way to visualize this strategy is as a reverse pebble game. Now, in order to compute or compute an expression, for instance, A plus B multiplied minus C, we must already have the temporary results of each sub-expressions. But this is equivalent with the pebbling rule, which says that in order to pebble or unpebble a node in the abstract syntax tree, all of its children nodes should be pebbled. We want, after the implementation of the circuit, to keep the results of the expression, but also uncompute all the temporary results. This is exactly the reverse pebbling game, in which we should have the root node pebbled and all the intermediate nodes unpebbled. Let us play with 2 different pebble strategies. The first requires a minimum number of pebbles, which is exactly a minimum number of concurrent temporal results that the circuit keep. Okay, so for the first implementation, we first pebble the children of A plus B minus multiplied by minus C. We can compute this operator, then we unpebble those because we won't have a minimum number of pebbles, and then we pebble the right part of the abstract syntax tree. And here we need, in order to reach to the root, 4 pebbles. Then we unpebble the right part. In order to unpebble A plus B minus multiplied by minus C, we have to pebble first its children, and then we unpebble the rest of the tree. So in this strategy, we used 4 pebbles, that is for concurrent operators, but temporal results. But we also used 15 operators because we computed and uncomputed those 2 operators 2 times. Another strategy, which is also called Bennett strategy, requires...
Sorry, we have a last 30 seconds, so please come to me.
Okay, yes. Minimum number of operators. And this strategy pebbles the whole circuit, the whole arithmetic, the whole tree, and then appends it. And in this implementation, we used 6 pebbles and 11 operators. That is 2 more pebbles and minus 4 operators. The second strategy contains a smaller number of qubits because each pebble requires some qubits. So it is worse according to width, but it's better according to depth. Fun fact, according to an interesting paper, for each number of k-pebbles, whether there's a k-pebble strategy is many one reducible to SHAT. Therefore, we can use a SHAT solver to find such a strategy for each k that is possible, and providing a way to trade off between number of concurrent temporal results and number of operations. I believe that this method is used in Classiq, or it should probably be used, but we only managed to implement Bennett strategy so far in uncompiler. Finally, I would like to mention that the minimum number of pebbles doesn't mean necessary minimum number of qubits, as some operators might require many more qubits, as the example provided here. So in this example, the minimum pebble strategy have 5 pebbles and uses 49 qubits, while the minimum qubit strategy requires 7 pebbles, but 46 qubits. That is 2 more pebbles, but less 3 qubits. Thank you for your attention. Any questions?
Thank you, Thomas, for the great presentation. What is the program that you made the slides with?
It's actually Microsoft's PowerPoint.
Ah, wow. So very well done. It was really a presentation in terms of the way you're presenting. So very nice and very nice work. I think it's an example of a different way of using Classiq. I think this and also the next project that will be presented, it's not the orthodox way when we think about Classiq, so how you can use it. But I think this kind of project, let's say like building a compiler, which Classiq offers a compiler, but sometimes people want to explore other compilers or to compare. So I think it's a very nice way to see how you can implement like another way of working with Classiq. So well done, very nice. Any questions from the audience? Comments? Okay, great. I think also the points and the challenges you incorporated, these are really challenges we face also with Classiq, to how to interpret the different registers and the numbers and like A+A, and how to actually tell the compiler to do it in the correct way. So it's a really nice work. Yeah. So well done, guys. And if there are no further questions, so we can move to the next group, which is group 21, integration of Classiq with Mitiq.
Good luck.
So group 21, who is the presenter?
Bill? I see Bill. You are unmuted. You are muted, sorry. Bill.
Oh, sorry, I couldn't share my screen there for a second. It's saying host disabled participant screen sharing. I had to reconnect from another computer. And that means that I think my previous login was allowed to share, but this current one is not. Can you allow me to share my screen?
You can share now, Bill.
Okay, got it. Okay, perfect. Okay, I'm gonna go ahead and share the screen. Give me 1 second here while you see the present. Oh, hold on 1 second. It's gonna switch screens here. Okay, let me know when you see the screen.
Perfect. We can see and we can start at 10 minutes now.
Okay,
Good.
and you can hear me? Perfect. Okay, so our project here is project 21, integration of Mitiq with Classiq. Some of the group that we have here, we started with a few more than what we have here, but it's Wally, Bill, and Tugba. So it's fairly short presentation. I had more slides, but we've reduced it down. So the objective is to determine if and how we could integrate Mitiq, the Mitiq error mitigation library into the Classiq platform. So just real quick, what is error mitigation? It's an alternative set of techniques to mitigate or reduce the effect of noise on the final results. And it's suitable for this era of NISQ. To try to tease out results from real hardware. Mitiq is a Python library that allows a developer to utilize various error mitigation methods. Some of those are zero noise extrapolation, probability error correction, digital dynamical decoupling, and another classical shadow protocol, which is another technique for trying to trying to tease out good results. Classiq, of course, is a platform for building, synthesizing, and optimizing quantum circuits, and it also comes with an SDK. So a little bit about error mitigation, which you've heard of. It's just a collection of techniques that are outside of what is done on the quantum error correction side, which is more at the hardware level. This is essentially performed on circuits before they're executed, and this is how Mitiq implements error mitigation. So there's several techniques that are available. A few of them are listed there. We researched or looked at ZNE, PEC, and DDD just as part of our research. So why do we need error mitigation? Just to give you an idea, this is from an execution in Classiq of a Grover A plus B equals 2. You may recognize this from the bootcamp or similar. You get some nice results here. You get 0, 0, 1, 0, 0, 1, 0, 1, or 1, 0, 0, 0, 0, which gives you the A plus B equals 2. The first two qubits, or the first two readouts, being the A and the second being the B. Now, what happens when you run it on real hardware? For example, here's that same algorithm run against, or circuit run against, the IBM Kyoto. You see that you get vastly different results, nothing that you could actually use initially. You do see some patterns in there, but you get basically results for every single bit combination, which is not something that you could technically use. That's why error mitigation is such a big topic right now. So here's a little bit more about ZNE. And just to give you a quick idea, what this technique allows you is you essentially introduce noise into a circuit, or the execution of the circuit, and then you use that noise to extrapolate backwards to a zero noise limit. So if you notice here, you might introduce a noise factor here, noise scale factor, which Mitiq allows you to do. And then using Mitiq routines, you can try to get to a result that would be evident when you used a zero noise limit. So again, you're just basically trying to extrapolate backwards for this ZNE. And that's one technique we looked at. Another one we looked at was probability error cancellation, and there's a quick description. We did some examples using this technique, but didn't dive too much into it. We mainly use ZNE, a little bit of PEC, and then towards the end, we were mainly utilizing DDD against the Grover A plus B equals 2. We also did some research on Classiq shadow protocol, which allows for error mitigation, maybe against probability distributions. The thing with ZNE and PEC is most of the examples dealt with a single value. For example, an estimation, or like what you might get out of a Hamiltonian energy, etc., not with noise distributions. With probability distributions. And it turns out that after consulting with Mitiq, it seems like their protocols that they implement don't actually address that. And the Grover A plus B equals 2 results in a probability distribution. So going down to Classiq, so some of the things that we encountered is there is no way to actually introduce error other than the bit flip probability in the GUI. So this is just a sort of a screenshot. That was one of the things that didn't allow us to integrate more tightly. So that doesn't mean that we could use Classiq's SDK for part of our experimentation. So what we ended up doing in that part is we chose an algorithm out of the Classiq SDK. Now, we didn't go as far as optimizing or configuring it any differently than what's out of the box, but that's sort of a piece that can be done in the future, is sort of enhance or optimize a circuit before we actually extract it. So here, we were also able to, aside from extract our circuits, we could also share them with each other and then import them using this particular feature. And here's the exportation. So here we basically would either export as transpile chasm or as chasm. Now, we did experiment exporting chasm 3 or chasm 2. Based on the circuit, if it's a parameterized circuit, it'll come out as chasm 3, which is something that we also looked at. Here's just basically, once we get the circuit out, we were initially using Qiskit's technique for taking a chasm that was exported and then utilizing it within our algorithms or our programs. But later on, we started using Classiq's API SDK get circuit, which is not highly documented, but with our advisor, we were able to make some use of it. So the main idea behind utilizing Mitiq is Mitiq allows you to create what's called an executor. Here you see IBM's executor, and essentially what you're doing is you introduce some noise, and then you pass it over to an executor that utilizes a certain stack. In this case, this is the one for IBM backend, IBM Q. What we did is we created two Classiq executors, one utilizing the API wrapper, which is not highly documented and took us a little bit because we had to use things like async IO for asynchronous calls. We also had to use some Lambda functions, which Tugba worked on. And then we also had to dig into the actual Classiq library to understand how to use some of the methods. And the second alternative we had is we created a Classiq executor using the model object and the execution functions, and that worked a lot better for us. It was better documented, so we were able to push through that. Here's just a quick idea of what we use on the API wrapper and async IO. So there it is again. If you notice, we're able to also utilize at least some noise models when we're passing into the API wrapper or the model executor. But that was the extent of the noise that we could introduce. And here's a little bit about the Classiq model again. We're using some noise properties that we were able to use. Now, some things to consider is some of the backends don't support the introduction of noise models. So that was sort of a hindrance to us, but we continued forward anyway. So one of the last things we worked on, which at least allowed us to sort of do some of the practice using our techniques of using the model executor in the Classiq SDK, was using digital dynamic decoupling. And essentially what that consists of is during these idle times of a circuit, this is the actual Grover A plus B equals 2 circuit. What DDD does is you select the types of gates that you want to introduce. A lot of times there's some common gates that are used like XY, etc., and identity gates. But what you're trying to do is introduce some decoupling by introducing gates here. And you can specify which types of gates to use and how they're actually splayed out within the circuit. And you're trying to do it during idle times. So something else that we had to consider is when we were running our Classiq executor is that depending on how we had the settings set, we were noticing that during transpilation that our gates would get removed. And so by the time they would get executed on the IBM hardware, our gates were gone. So we had to basically tone down, either select transpilation option none or light or medium. And there's two places where you can set that transpilation option. One is in the execution and one is in the synthesis of the circuit. So those are some things that we sort of had to overcome as we're going through there, things we discovered as we're doing something simple like just using IX gates. Some other things that we have to consider are...
Sorry,
yes,
we have last minute, so...
1 minute. Okay, I'll go real quick. So some other things to consider is we have to concern ourselves with the types of gates that are supported by the backends. Here's some just an idea of the gates that Mitiq suggests, some experimental gates that we saw in other research papers, and then some of the ones that we were trying. Ideally, all these gates have to equal out to identity. So essentially, you're not really changing the circuit. You're just introducing some circuits that sort of cause a disruption. So you'll see here some runs against the IBM backend and some of the different gate combinations that we tried. You will see here that we didn't get complete results. You'll see some patterns, but we're not seeing anything too, I think, useful at this point. So some of the reasons we weren't able to fully integrate Mitiq into Classiq, so we've got some of those listed there, aside from the bit-flit estimation. We did try some second quantized Hamiltonians, and then we weren't able to make direct changes to the Classiq SDK, of course. However, we were able to create the new two Classiq executors. We ran many experiments using DDD, and we learned how to use Classiq synthesis and execution options. Learned about noise properties, etc., and how to inject noise. Now, for the future, we've got some items listed here. We're looking to continue experimentation, specifically in trying to get some better results and maybe using some of the other techniques with some of the other circuits that are available through Classiq, and then study some other gate combinations and utilize possibly some post methods on IBM's backend. And that concludes the presentation. Thank you.
Thank you, Bill, for the great presentation. We have time for maybe 2 questions from the audience. So are there any questions? So I can start. So now with the 2 executors that you define, basically anyone can take them and use them as adds-on to Classiq and then use Classiq with Mitiq with your executor?
Yes, definitely. In fact, there might even be some suggestion in the future to discuss these with Mitiq, the maintainers of the Mitiq library, because they have examples or backends, what they call integrations with Cirq, PennyLane, most of the other quantum providers, but they don't have anything listed for Classiq. This would allow them to basically put this on their site and say, we can also utilize Mitiq with Classiq using the model. I think the model turned out better than the API wrapper, but still, yeah, it would allow a way for Mitiq to now support Classiq as well.
That is great. So we would be happy to continue support this in any way, and then to integrate Mitiq with this. That's a great initiative. Interesting. And I would also want to know your high-level view on error mitigation as a whole. So now it seems like the ecosystem is moving a bit more towards quantum error correction, but still error mitigation will continue to evolve both on the control pulse level and on the digital level. So I was wondering, from your impression in the last 3 months, what do you think about error mitigation?
Well, I think it's still something to pursue. I didn't find too many papers that deal with the actual implementation of error mitigation. You find a lot of theory. There's a lot out there. I did find 2 that deal specifically with running error mitigation on IBM hardware. But I think with the advancements of the modalities, in other words, as quantum computers are getting better, I still don't think that they're at a point where error mitigation will not be used. I just feel like even now, currently, there needs to be more experimentation done in this arena, because as you see, the results are nowhere near what we need. I mean, a lot of what I've seen done in the quantum computing arena is done on simulators, which are great for proving the theories and proving the algorithms. But when you actually get time to execute them, even with the work that I do on the image processing side, the results are non-usable. And I think that a lot more needs to be poured into the error mitigation realm.
Okay, interesting. Thank you for your take. And yeah, we in Classiq will be happy to continue support also the integration with Mitiq, and if Mitiq wants to incorporate these executors that you've done and you defined, so it will be great. So thank you for the presentation. We can move to the next group. So group 32, option pricing in Classiq using quantum amplitude estimation.
So is my screen visible? Am I audible?
Yes.
Okay.
Perfect.
So shall I start?
Yeah, we started 10 minutes now. Good luck.
Okay. So good evening, everyone. So it's my pleasure to present to you the applications part of Project 32. So where I've been working on option pricing, a finance application of quantum amplitude estimation algorithm with Classiq SDK. So these are the broad project aims that I tried to work on during the course of 3 odd months. It started off with the complete mathematical development of QP and also QE algorithms, and then using these for option pricing. I've also been trying to build an option pricing tutorial using Classiq SDK. So I would like to start off with a very quick review of the algorithms used. Starting with QP, the goal is to estimate the phase theta obtained when a unitary operator U acts on a quantum state small u. So below is the circuit used for this, where the top register with n qubits, which is called the estimation register, and n depends on the precision of the phase we need. So the lower register will have the quantum state u, and then you add the powers of controlled u operator. Then we do an inverse Fourier transform on the estimation register, followed by a measurement on the estimation register. So we repeat this experiment for a number of short times to get an outcome state with probability to get an outcome state whose probability is maximum. And let's call that state y. And from this, we can estimate the value of theta using the formula below. So this is the quantum phase estimation algorithm. So next, I want to explain you quantum amplitude estimation, so which uses quantum phase estimation algorithm. So the goal here is to, so suppose you have a state psi obtained after an algorithm A acts on a 0-qubit state, and suppose we can decompose the state psi as two terms, one as a good state and one as a bad state. So the goal of the QAE algorithm is to estimate the amplitude associated with the good state specific to our problem. So for this presentation, consider the second term with the rightmost qubit 1 to be the desired state, and QAE will estimate the value of A. So for this, again, we use the Grover's operator, which from a geometric point of view rotates our state psi towards the good state psi 1. So at a very high level, when you act Grover operator on psi, what happens here is that the amplitude A gets encoded as the phase theta, and we evaluate this theta using the quantum phase estimation algorithm. So that's where the QP part comes in. So how does this work? Just like the previous QP circuit. So instead of controlled U, we have the controlled Grover operators, and then an inverse quantum Fourier transform, and the measurement on a estimation register will give you the state Y where the probability is K, and then we substitute this back in the expression to get the value of A. So we are now going to use this for the application of option pricing. So what are options? So options are basically financial contracts whose value is decided by underlying assets, say stocks. So it has a date of expiry and a stock price target, K. So this is also called the strike price. For example, if you look at a call option, so if the stock price S surpasses the predetermined target K before the expiry date, the buyer profits S minus K. So this is called the payoff of the option. Payoff. So the stock price S, they change stochastically, and the goal of option pricing is to determine the average payoff of option contract at maturity. So classically, we use Monte Carlo simulations to do this. So let's say we have the vector capital X that represents the price path of all the stocks in an option contract, and let's say there are m possible price paths. So which means there are m different possible X vectors, each with some probability P. And let's say each vector X, we have a payoff f of X, then the expected payoff is can be written by the simple formula here. And we are interested to calculate this expected payoff using the amplitude quantum amplitude estimation algorithm. So these are the parts involved. This is the brief methodology. So first we load the probability distribution. Next we load the amplitude, and the amplitude, if you see the equation 2, it involves the payoff, and an ancilla qubit is used here. Here we assume a European call option. So this is the expression for it. If I is the stock price at expiry and it's above the target K, the payoff is I minus K. Otherwise, if it's below the target K, the payoff is simply 0. So once we have the state prepared, so we can see that the probability of the good state, here the second term, probability of the good state, the state with qubit 1, will give us the desired expectation value, which we call A. So these are some parts of Classiq SDK codes. Here I used only 4 price paths, and both distribution and amplitude loading is done in a single function here using Classiq. So for this demo, I choose the strike price of 70, and the price paths start from 45 and end at 87.5. So between 45 and 70, there is no price, there is no payoff because the strike is 70. And post that, there is a payoff of stock price minus 70. So that's what the affine parameter. Does. So it's useful to note in this code that the piecewise linear amplitude method which has been used, does not exactly create the state in equation 2, but it creates a state with some scaled value of the payoff. And hence even the A calculated here is also scaled, which needs to be rescaled for the desired answer. So this is the circuit that is generated using Classiq after the first step. So this includes the state preparation part and the amplitude loading part. Now we use the quantum amplitude estimation algorithm to find the probability of the desired state, which we called A. So we recall that the quantum amplitude estimation had the Grover operator, which will pick the state with the rightmost qubit 1, which is our good state. So that's what the arithmetic oracle does here. Then we take all these building blocks together and synthesize our model and generate our circuit. So this is what the circuit looks like. So these are the two main parts: state loading of the state distribution as well as the amplitude loading part, and then we apply the phase estimation part. So this is how the phase estimation blocks look like when you open it up. So you have the Grover operator and you also have the inverse QFT on the estimation register. Here there are three inverse QFT operators because I've used three estimation registers. So and after the measurement on estimation register, so actually to generate this specific histogram, I used the estimation register of size 4, as you can see on the x-axis. So we pick the state with maximum probability as told in slide 1. Here you can see that the peak is at 4 or sometimes at 12. So it doesn't matter which you choose for extracting the results. So we call this state Y, so either 4 or either 12. So and this we substitute in the expression sin square we saw earlier. And this is what the function here does. And we get the value of E. And this is the scaled expectation value. So recall the second equation that prepared amplitudes with some scaled version of the payoff, and we'll get a scaled expectation value, which can be rescaled in this last code block, and we get the value 8.5. So of course, this result doesn't seem to be very good. As you can see, a simple theoretical calculation would give us a result of 6.125. And from QA, we got 8 point something. Actually, I did use post-processing, but the results weren't improving. So more exploration on this front is needed. So this leads us to the future plans, parts of which were intended to be completed in this project, but could not because of certain constraints. So I plan to demonstrate option pricing efficiency using post-processing for multi-asset options and also different types of payoff using Classiq SDK, and also make a more complete, option pricing tutorial using Classiq SDK. So as part of this project, I also worked on, making a detailed option pricing tutorial, which is now at a very preliminary stage, and more work needs to be done, especially to include things like post-processing, etc. So I'll just quickly scroll over this. So I plan to include all the mathematical details and also the stepwise implementation of the algorithm, and also proper, accuracy comparison and all that. So again, I have to continue working on this, and I hope this will be very useful once completed. Yeah, with this, this was it, and I would like to thank my mentor Ron Cohen for guiding me throughout the project, and also a Classiq community for helping me with the doubts on Slack. So I also thank QWorld and also Abu for this opportunity to take part in this very useful course of QWorld. So thank you very much.
Great, thank you, Raj. Thank you for the great presentation. So I will start with a question. So maybe I missed it, but let's say in slide 11 that you showed the circuit, is it the implementation using the built-in option pricing of Classiq, or it's you built it from other building block in the SDK?
Okay, just let me open my presentation. Can you which is the slide number 11?
Yeah, so for example, the circuit that we view now, this is from the built-in implementation of Classiq option pricing, or is it?
No. This is not built-in implementation. This is something I implemented using built-in functions of Classiq, but option there was a built-in function of Classiq. I don't remember what's the function called. I didn't use that. So this is something which that I prepared from like the scratch.
Okay, great. So very nice. And yeah, I think it's a great implementation. And if I've seen correctly, so in the tutorial that you're writing, it's with all the SDK of Classiq.
Correct. So yeah, here also you can see that I've built everything from the scratch. I've not used the built-in option pricing function.
Yeah, great. So I think like doing a tutorial on the thing is great, and I think it can be really, really useful. I highly recommend you will adapt it to the new QMod and the new basically SDK. I think it's orders of magnitude more efficient and more valuable to do it in the new QMod.
Okay, so would that use all these inbuilt functions which are used here, for example, grower, operator, and all that, or will it be completely different? For example, this function and all those.
Yeah, that's a good question. Some of the functions you can use, some of the functions you can build. I think almost all the functions you can use also with the new QMod, but all the integrations and all the controls and all the wiring, it's orders of magnitude easier and nicer to do.
Okay.
Yeah, Ron?
Yeah, regarding what you suggested, Ed, and really Viraj made an amazing work, a tutorial that we have a Quantum Monte Carlo tutorial in the user guide, but Viraj made something which is much more detailed and well understood, and I wish we had such a tutorial in our user guide. I'm not sure if Viraj will have the time and the ability to change it to the new language, which is not yet complete, but I think it will be very efficient for us to try to insert it before the change to the new language and to take us the mission to interpret it into the new QMod, because it could be really helpful for finance documentation.
Yeah, that's great. In the short time, we will move all our tutorials to the new QMod. So if already it can be adapted in advance, that would be great. But I think in any case, it would be useful, the tutorial that you've written. I think detailed explanation alongside implementation, it's really good.
Yeah.
Great. Other comments, questions from the audience? Okay, cool. So thank you, Viraj, for the presentation and the implementation. I'm really looking forward to seeing more the development and the tutorial itself. So thank you. And now we can continue with group 26, an introductory course with Classiq.
Hello, I'm sharing my screen. Well, okay. Our project is about designing a course, an introductory computing course, but we find another situation very interesting. Now, quantum computing is rapidly expanding into all fields of scientific research. Until now, researchers in other fields, imagine a Mitiq, a physician, a surgeon, a person who makes only plastic surgeries. And tomorrow appears a big quantum algorithm to medicine, okay? They cannot develop low-level code and can be users of current common products of quantum computing, but they can be users of Classiq, because Classiq can develop a new built-in algorithm to medics, to surgeons. Imagine that this exists. So this group of researchers or professionals that can't understand mathematics, can't understand physics and computer science is a new group of potential users of the Classiq platform and potential researchers in quantum computing. But the issue is how to reach them, how to obtain the knowledge they need. Until now, the current educational tools are not adequate. It's impossible to teach a mathematics, quantum computing to our medical surgeon, to the healthcare people. But there is a good, the best solution until now for quantum education is the QWorld solution. That simplifies a lot the things because it's based on theory of probabilities instead of basing of quantum physics. So it's better, but our medic, our physician can't understand low-level languages, can't understand computer science. But what we can do, we can integrate the Classiq platform with the QWorld methodologies, the best products in the market, the Classiq platform and the QWorld methodologies, to obtain a new methodology designed for our medical person. It is not easy. It is not easy because if we can put the physician in front of the Classiq platform, yes, he will be using the platform. We can change the parameters, we can set constraints, but will not understand the difference between a classical program and a quantum program. So the idea is to design methods, new methods of education to people who does not have our kind of brain, another brain, another different brain. The strategy is to observe the process from the point of view of the older researcher, of the older person, to make possible the understanding of the principal concepts about quantum computing and the difference between a classical algorithm or a quantum algorithm. This is a process that we have analyzing in the development of this course. This is the contents of the course. There are many introductory parts about quantum computing introduction, the Classiq platform explained in terms of Classiq constraints, a lot of videos that we have here in YouTube, published. Here is Rishi that published the videos in YouTube. We have developed a notebook, Jupyter notebooks, about all the state preparations in Classiq, and we have developed these quantum algorithms. The Shor's algorithm is the last today added to the course. The course is all based in Jupyter notebooks. It's complementary to QWorld. As you see, there are videos. The notebooks are 32. Here we have our content, 32 notebooks, but I can show you only something idea about how to show some concept exclusively by using the Classiq platform. I want to show what a quantum Fourier transform is to our medic, to the physician. what can I do with the Classiq platform, exclusively with the Classiq platform, to show how does this work? Okay, I show a QFT, a quantum Fourier transform with only one qubit. It's very simple. The medical can do it. Quantum Fourier transform and put a 1 here. Okay, so he can see that the circuit is a Hadamard gate. Then we tell the student, please repeat with 2, 3, and 4. Very simple. Can do it the Mitiq. This, okay? This is with 2 qubits, appears a new block, and a swap, okay? With 3 qubits, a new block with a new phase rotation, and 4 qubits. So we show what happened with 5 qubits, and the idea is that the person recognizes a pattern. It can't understand what is each of these boxes, but can see a pattern that we remember as a quantum Fourier transform, okay? Medical people, people who is based in another science, many times don't have our kind of brain, our thinking. We need causal demonstrations. We can't understand anything if don't demonstrate, see the demonstration. But these people, another researchers of another sciences, what needs is only correlations, not causation. In his brain is very useful, very common to have correlation. So this person have understood something that we'll see in the last formula of the demonstration. He can't understand all the steps of the mathematical demonstration, but we will show the last step and we'll see, oh, okay, this is what I see in the platform. This is my circuit. And what is the objective of this? What does the QFT do? The quantum Fourier transform do? So we can see, show something similar. We prepare the states as a periodic function, and then we show how we obtain a frequency representation. It's very simple to see in the graphic, in the output. That is a frequency representation of the output represented. Okay, and this.
We have 1 more minute.
Okay, I am finishing. Okay, I think that this can be understood in this way, but persons from another very different areas, and this is a big job, a hard work. Why? Because it is necessary to adapt each algorithm of the Classiq platform to find a way to communicate the best strategy to communicate to the users of this algorithm the essential steps, the essential ideas. And so this, as you said, will cause a kind of democratization of quantum computing knowledge in areas of research and of the industry that in this moment are excluded of the knowledge. well, that is all. I think that we think that this will produce a worldwide global dissemination of the Classiq platform and this knowledge about quantum computing. That's all. Thank you.
Thank you, Alvaro, so much for the presentation, and thanks to all the group and Nati, the mentor, for the amazing work. I think definitely the direction, and as you said, the presented the ideas that Classiq is useful for quantum researchers, but also for other quantum enthusiasts that want to enter this domain, and to be as a first step is absolutely right. And definitely we want to take it forward. And also even nowadays, you said that you have 32 notebooks. So even nowadays we have many educators that want to teach quantum courses, and they are coming to us for materials and how they can use. So I think these 32 notebooks can be really a great resource. So even today you can share it with the community and via Slack and via everyone, and tell people that here are some materials that they can use for teaching Classiq. So that would be great. Yeah, and I'm looking forward to see further development and how we can take it forward. Any questions or comments from the audience? Okay, so I have one. Can you share please again the syllabus basically of the course, or where you add all the notebooks?
What do you?
So with from the Jupyter, you had like a list of all the notebooks that you have. According.
Yes, of course. Yes, I will show. Here is the list of the notebooks. Okay. Well, here are the links in but you can see in the presentation here the list. Here is the introduction, the introductory part, the state preparation, cover all the algorithms of the Classiq platform, and this list of quantum algorithms. The Simon was developed at hand because there are no built-in function. In other cases, we use the built-in functions.
And for example, can you show me the notebook of the phase kickback?
Phase kickback. Yes, I suggest that Rishi. Can you show? Or because he developed this notebook, I will show the phase kickback. Here is it. We have a video. Here is explain it.
I see. Okay, that's really nice.
But
nice.
Yes,
nice.
We have. In this case, there are videos, but and the tasks are optional. But in many other, we have paid independent Jupyter notebooks with the solutions of the exercises. Okay, there are 33 notebooks in total. Here are the solutions. Here is the program developed, the idea of the Simon algorithm. Yes, it's a good job. It's okay, but I think that it can be better.
Yeah,
can be improved.
Yeah, but really nice. So if even today you can start sharing it with the community in our Slack, that I think it will be really useful for educators
Sure.
nowadays.
Yes, it is shared. This is I made it public. You can everybody can see this course, can download, and all the videos that are here in YouTube, publish it by Appreciate. So we can share this to all the community. Okay.
Perfect. Thank you so much, everyone, and all the team. Well done. And now we can move to the next group. So the third presentation of group 32, QP for the ground state energy of a particle in a double well potential. So you can share your screen. I'm not sure who is the presenter. Perfect. I can see the screen. I cannot hear or see the presenter.
Hi, can you hear me?
Yeah, I can hear you. I cannot see you. I can see the screen, but I cannot see you.
Presentation. Okay, so sorry, my camera is not functioning properly, so I turned it off, but they seem to have a problem with my camera. Okay, so my presentation is about estimating the ground state energy of a particle in a double well potential using quantum phase estimation. And the outline of my presentation is this. So the goal of this work was to simulate and determine the ground state energy of a particle in a one-dimensional potential. So what can be said is that the technology advancement have facilitated more precise simulation of quantum computer, and the release of software like Qiskit and Classiq provided researchers with a pivotal tool for quantum computing research, enabling algorithm execution on quantum computer. And since then, significant advancement in simulating quantum system have been made. And there is the study by Schirman et al. Published in 2022 on finite square well potential, in which they estimated the ground state energy of a particle in a finite square well potential, and that demonstrates the utility of quantum computing in modeling simple quantum phenomena. But however, there is a growing interest in employing quantum technique for complex system simulation. So our research, the work we did, focused to a more complex potential than the one used by Shoki et al., which is a double well potential in one-dimensional Schrödinger equation. And for this research, we plan to utilize Classiq platform as well as IBM to simulate and estimate the ground state energy for that potential. So there were some challenge. For instance, our potential is more complex, which we had some difficulty in implementing this, running our simulation, especially using Classiq. So the aims of the quantum phase estimation is to estimate the phase of the eigenvalue of the unitary operator, which is written exponential of 2 pi I theta. So when we consider a particle in a double well potential, we know the Schrödinger equation is given by equation 1, where the Hamiltonian is given by equation 2. And so in this study, for simplicity, we consider h bar equal to 1 and m, the mass of the particle, equal to 1 as well. And the solution of the Schrödinger equation 1 is given by equation 3. From that equation, we can define the unitary operator u of t, which is equal to exponential of minus ht. And if we compare this expression with this one, then we see that we can express the energy by equation 5, which depend on the phase theta. So meaning that for us to get the energy of the particle, we need to estimate the phase theta, and then we can calculate the energy of that particle. So what we need to do here is to construct the time evolution gate, and for that we need to decompose it. Now, since in this equation, we can see that our Hamiltonian is a function of P and the potential V of X, the momentum, and the potential, which itself is a function of the coordinate. And since the potential and the momentum do not necessarily commute, so we use the second order Trotter formula, which allow us to expand the unitary operator, and we obtain the expression given by 6. So then we apply this unitary operator to the initial state at t equal to 0 in momentum space, which give us equation 7. And since our kinetic energy depend on the momentum, that means we also need the Fourier transform for us to be able to represent the quantum gate of this Hamiltonian. Okay, so to represent the quantum secret for the kinetic energy term of that unitary operator, we simply apply it to the state J, and we obtain equation 10. So from that equation, from the analysis of that equation, we can see that the third term is just a constant factor, and it can be applied using a constant phase gate. But the middle term can be simplified as shown by equation 11, and it can be implemented using a simple qubit phase shift gate. So with regard to the first term, it can be implemented using a simple phase shift gate and a 2-qubit control phase shift gate, which are, like shown by equation 12 and 13. So after analyzing and decomposing the kinetic energy term, we have represented the quantum circuit, which is depicted in figure 1. So next, what we needed was we needed to represent the potential energy term of the time evolution operator. So for that, we use the same process as before. So, and then we obtained the matrix given by equation 15, where V0, 0, 0, 1, 1, 0, and 11 are just average potential for the state 0, 0, 0, 1, 1, 0, and 1, 1. And the quantum gate representing that term is displayed in figure 2. So, like I said, our approach was to use the quantum phase estimation to estimate the phase and then calculate the ground state energy. So on this slide, we show how the quantum phase estimation, we give the step to estimate the phase using the quantum phase estimation algorithm. So we start by applying n bit Adama gate to the first n register. Then we use the control U gate, and then we apply an inverse quantum Fourier transform, and then we measure the we do the measurement. We can also use the iterative phase estimation algorithm, and which the steps are given as follow. I will say almost the same than the previous one. We apply a Adama gate to the initial state, and then we apply the control E operation. Then we apply again an Adama gate to the work qubit. We repeat a phase gate to estimate sine of theta and cos theta, which will enable us to then determine theta, and we repeat the measurement. So our goal was to implement this using Classiq platform, and also IBM a simulator. But with Classiq,
sorry, we have 1 more minute to go.
With Classiq, it was not straightforward because for us to implement it with Classiq, we needed to decompose it in quantum gate, which is not straightforward because of the complexity of the term that we obtained for the quantum for the potential energy and the kinetic energy. So because of that, we decided to pivot to IBM, and to approximate our ground state wave function, we use equation 4, and the figure 3 show the ground state wave function. In figure 3, we plotted the ground state wave function as well as the Doberwell potential, and we can clearly see that they are symmetric. So for our simulation, so we choose our parameter as follow. We choose a time step of 0,02, a time ovulation of 0,06, and we run our simulation 30 times, and the average potential, with those average potential, we obtain the ground state energy equal to -6,744,98,4. So we compare this result.
I'm sorry, we are over time. So if you want last sentence, but we are over time for the presentation.
So to conclude this work, we will say that initially we wanted to do this simulation using Classiq, but because of the complexity of the term, we couldn't. So we decided to do it with Qiskit first, and then now try to implement it because of the time constraint. Now try to implement it using a Classiq. So
thank you.
That is what I have to say.
Okay, thank you. Thank you for the presentation. So I have one question. So what do you mean? Like, what was the specific challenges that you were facing in trying to incorporate it with Classiq?
Okay, so if I come back here, so the challenge. Okay, so it's coming. Okay, I don't know. Give me 1 minute, then.
It's okay. Maybe if you can just say it on the high level, because we don't have a lot of time, but just like in 1 or 2 sentences, what exactly you were facing as a challenge when you try to implement.
The challenge I face here was to decompose this term, because you can see that these terms are very complex. So in order to implement this using Classiq, this matrix needs to be decomposed in gates. In gate X, Z, and so on. So which was not straightforward. So that is why I decided to start with Qiskit because of time constraint, like I said, because I just had a limited time. So, and then after doing it now, go back and try to implement it. I mean, to express this in terms of quantum gate in order to implement it, to be able to implement it using a Classiq platform.
I see. So what you were, the challenge you're facing is trying to incorporate a specific unitary matrix into.
Okay, yes, now it's working. So we can see here that this is, okay, so these are built-in function provided by Classiq. And we can see here that we can, in order to implement this, we need to express, like I said, those matrices using the quantum gate like X and Z, Y and Z. It's the same for the kinetic energy term. So you see that we need to decompose those matrices using Police operator, which is not straightforward. And
okay, I see. I understand. Okay. Okay, great. Thank you for the work and the presentation and for taking the question. Thank you, Pacom. So now we are just on time for the last group of today and for this session. So group 28, signal processing primitives with quantum algorithms. So please, if you can share the screen.
Okay, I'm sharing the screen. Share sound. Share. Is my screen visible now?
Yes.
Yes, okay. Let me minimize this controller here. I don't know how to minimize it. Okay. Our project 28, signal processing primitive with a quantum algorithm. We have Galvin.
Sorry, maybe you just can press on the slideshow and then it will be in a large screen.
Yes, I know, but I have to move to the different so that I can present well.
Okay. Okay, so starting the time. Good luck.
Okay. We have a Gal winner as our team leader, and this myself representing myself from Nepal, and Ibrahim from I don't know, I forget his country. Okay, our presentation flow will we don't take too much time. The flow will be like we first have overview of a signal processing, image filtering that we have in the classical world, mean filter, and our algorithm, and conclusion and possible modification that can be done. Okay, what is signal processing? Okay, signal processing is a field of study that focuses on analysis, manipulation, and interpretation of the signal. Everything that we deal in our real world is a signal. Here we can see there is a noisy information where we have processed and have a desired information. Okay, why is signal processing? Signal processing is important for several reasons across the wide range of a field. Here are some reasons: information extraction, noise reduction, and communication system. We mainly our project mainly deals with the noise reduction on the images as we deal with the image, and the communication system, which is one of the most research field. This is the one of the signal processing system that I have been working on, the classical system. So I am just okay. Image filtering that we have in the classical world. We have a mean filter, edge detection filter, median filter, and many other. But one of the most popular one are these. We work on this mean filter, blur or smoothing filter, which removes the high frequency noise by averaging the pixel value in the neighborhood. Okay, we work with the signal processing and develop our algorithm on hybrid realization of a quantum mean filters with the different size and Yakaryilmaz image and the QFT based operation. Okay, what is the mean filter? Mean filter, also known as average filter, is a common image processing technique used to reduce noise and enhance the quality of the image. Here we can see take this block as a reference, and this is an unfiltered value. While taking the average while adding this and averaging it, we get a new value for this pixel position, and we just replace this pixel position with this value, and with this go all with this depending upon the kernel size or the window size that we have taken. Okay, hybrid algorithm. That algorithm for the mean filter, we first convert the image to the NISQ-Era image. Then we apply the filter algorithm. If pixel are on the boundary of the image, then we simply copy it, and if it's in the boundary, we simply copy its edge. It does not have this required column and the row, so it's missing, so we simply copy it. And otherwise we apply the QBXY circuit. We evolve we evolve the quantum circuit with this algorithm, and then we measure the circuit, filter out the pixel which value are of the probability up to this, and we reset the array and convert array back to the image. Sorry, here there was a typo. Okay, quantum image representation. There is a we work with the NISQ-Era in the NISQ-Era. We first work with the NISQ-Era, but we found that NISQ-Era is more efficient. So we shifted to the NISQ-Era image representation. Here in NISQ-Era, this is the NISQ-Era circuit representation, and this is the NISQ-Era circuit representation. Okay, why do we choose NISQ-Era? This is the sample image. We took a small image so that we can process it fast. Okay, now here we can see the program info for NISQ-Era. Depth of the program is 125, where for the NISQ-Era there is depth of 111, and we can see that other gate count also is also less in the NISQ-Era images. And this is the result of the execution of the NISQ-Era and the NISQ-Era image. Execution result of NISQ-Era, where we can see that there is no equal probability of the outcome. Here we can see that some of the outcome are with the high probability and some are the less. But with the NISQ-Era, we almost have the equal probability. So we chooses this NISQ-Era images. This is the execution result of the NISQ-Era images. This we have the almost equal probability. And this is the implementation. Okay, sorry, we have to reconnect it. Okay, and we have a copy model. Yeah, we go through the some of the arithmetic that we use in this algorithm. So we have a copy model. For copying model, there are the two states. One is for quantum tunneling and other from the series of a control gate. Okay, from quantum tunneling, if we copy the state, now we just lose the state of this from the wire or the state we copied. So circuit for the quantum teleportation, but the problem is we will lose the value from which we have teleported. Thus it is incompatible with our project. So we have to track the every times project. Yes, we have to track every image many times. Like when we filter this part, then we have to assess this image, and also when we go through this part, we also have to assess to this. So this quantum teleportation won't work with our project. So we go through this using the series of a circuit of a control gate. Okay, the question arises: doesn't this violate the no cloning theorem? Okay, no cloning theorem state that it is possible to create it is impossible to create an identical copy of arbitrary unknown quantum state. No cloning theorem is a general representation. CNET not only can only copy the certain state. Those are in the computational basis 0 and 1. This is allowed under the no cloning theorem, which only prohibits copying the arbitrary state. It can copy the arbitrary copy. Since we are working with the NISQ-Era, which is in the Z basis operation, and there is no probabilistic representation, so copy model the copy model does not work if we work with the probabilistic representation of image like FQ-Era and other which incurs on the X basis. Okay, simulation of a copy model. Here we in our project we copy from the IREG register to INREG register. Okay, where is that? Okay, control copy. First I will from this. Okay, this is the original cube image. This is the qubit where we store the original pixel and okay, where is that INREG? I have And this for this iron rig, we use this iron rig for this for storing the filter image pixel value. Okay, and where we copying only the two state, we copy the two state here. Okay, wondering why there is a 0 0 for the rest of output, since we are dealing with the mini qubit many position. Initially the iron rig is assigned with the value 0 0 for the every pixel position. When we copy it, then it will be displayed here. Okay, I will show. Okay, copy only copy. Here you can see that for four images we had 0.75%. That means 3 of the state with the 0 0 state, and the 1 of the state with the with this pixel value. Simulation. Okay, cyclic shift operation, one of the most needed operation that we have to use in this project. It is a bitwise operation that involves the shifting the bits of a binary number to the left or the right by specified number of the position. Okay, if this is the image and we do the cyclic shift right, then this pixel position will shift to the right, and if it's at the end, it will be rotated and will be at this starting, which is shown here. And similar to the cyclic shift right, no, it's left, cyclic shift y right, sorry for the typo. Okay, I will show this demo also. Okay, first I will show. Okay, when we what happen if we copy the same state twice? Okay, same state twice, copying same state twice, we will receive it just cancel out each operation, so we will receive the 0 0 with the 100% probability. Now after only copy. Okay, now copy. When we copy this 0 0 state, if the cyclic shift right operation doesn't work, then we will be expected to receive 0 0 with the 100% probability. But when we apply this cyclic shift operation and have this same copy state, it will give a different result. Cyclic and copy. Okay, we will have, as expected, we have a two different we have a two different output. Two different output. Now copying, now let's focus on this. We first copy this 0 0 state, and then we have a cyclic shift right.
Sorry, Rishav, we have 1 more minute to go.
Oh, okay. And then we again this, so copying from the different state, it should cancel out. So okay, copy from the different from the same, so we get we cancel it out and we get the 100% probability. Okay, now this the QFT for the addition, we use the QFT based addition, which is already provided by the Classiq platform. So okay, now working of our algorithm, we first we have this image. We just considering this 4x4 image with the 3x3 kernel. So we are leaving this boundary as they have the missing rows and the column. And for this, A11 and A11 each copies with each other, and everything so goes like this. So for 82, it copies these this according to the kernel size. It copies A11, A12, A13, A21, A22, A23, A31, A32, and A33, and kept it into this value, and similarly goes through this. Okay, after that we use the classical normalization technique, where we measure the circuit. After this process, new images are obtained with the weighted pixel are added in the pixel, and then we filter out the value with the probability of this and convert the binary value obtained into the decimal, and we normalize. Since we have to divide, we have added 90, we have added the different pixels, so we divide with this size, and this is the outcome of this image. Okay, possible outcome with the different circle. If this is the original image, then using the different size for the...
Sorry, so maybe concluding words, because we are out of time.
Okay, only this slide. Okay, this future work, working with the GQR model, we can represent this this and everything. And for everyone, I have kept this algorithm on my GitHub profile, where you can change. Here I have written the to-dos, where you can fork and create an issue so that we can improve this algorithm. And okay, finally, I have to show something. Okay, after the mean filter, we run on this real hardware device, we get this outcome, and that's all. Okay, thank you for listening. I think I don't take the time. Okay, any question or something, sir?
So thank you very much, Risav. I think the work in general of signal processing and what you have done, and in general signal processing techniques with quantum algorithm, I think it's really interesting, a research and exploration venue, and I think you've done really nice work with many primitives. And yeah, it's really nice, the collaboration, and I think you can also promote it in our community and tell people to see the work and what you have done and to contribute for this. Maybe we have time for one question from the audience if we have. And if not, yes, so we'll
yes,
so we think
yes, I have NISQ-Era and ENISQ-Era both. We have coded that everything. Here ENISQ-Era, and after that I have the here NISQ-Era. I bought the circuit. That's all, I think.
Great. So thank you, Risav and Ibrahim. Thank you for the work. Yeah, and we are coming to conclude. So Yuda, I think you're unmuted now.
Yeah, I asked to unmute. I want to say a few words. My name is Yudanov. I'm the CTO of the company of Classiq. I kind of wasn't the background, but I've seen this work going on for like 3 or 4 months, and I was really amazed, astonished with all this work going on. I was following closely with the mentors and with the students, and now, actually I wanted to say welcome words in the beginning, but I was muted, so I'm so happy that I have the chance to speak now, because I've seen the presentations, each one of them, and they are completely beautiful and wonderful. So much work, quality work done in small time by enthusiastic people. So really, first, thank you for those months. We learned a lot from you. Thank you to the mentors, to the Classiq mentors. I think everyone, the students and the mentors, did a great job. And absolutely, of course, thanks Abu, and thanks Eden for your extreme leadership on this. It was an extremely fine program, in my opinion. And to all students, keep up this spirit. That's the most congratulations word I can tell you. Just keep up the spirits, be our fine ambassadors, and I'm just looking forward to your success and to your continued interaction with us wherever you find yourself in your successful career. So thanks again, Eden, Abu, and everyone here.
Thank you, Yuda. Thank you for the words, and yeah, I'm resonated with Yuda's words. I think the course overall was amazing, and well done to all of you and the mentors and Abu. I think it was a great success, even though we along the way we overcame challenges and high-level challenges from that are way beyond our control. But I think overall it's a great success, and the presentations today, they really demonstrate it. So well done, everybody, and thank you very much.
I totally agree. So at the end, yeah, so these presentations are really great. Thanks to everyone. Yeah, it was long time, 4 months, but at the end, we all did. Congratulations.
Yeah, well done. And the Classiq community and the Classiq platform, and we are all here and we are going to be here. And so please, as Yuda said, keep up engaging with us and with the community, and anything you need, we are more than happy to help and support. Yeah, and I'm looking forward to seeing you in future events and future community engagements.